Hello viewers, we're going to now taking you through the story for A-level applied mathematics. And this video, we're going to go through the topic of resultant and relative motion. So this topic is under mechanics and is suitable for students in both senior 5 and senior 6 offering principal mathematics as part of their combination. So before we start, let's first look at the course outline so far. So math paper 2 or applied mathematics is divided into 3 parts. The first part is mechanics, which is also further divided into 3. So in mechanics it's divided into 3 parts. The first part is kinematics, where one comes in section A, one in section B, and these are the topics. The second part of mechanics is called dynamics, where one comes in section A, one in section B, and these are the topics. The third part of mechanics is called statics, where one comes in section A and one in section B, and these are the topics. That means that in overall 3 come in section A and 3 in section B for mechanics. Then the second part of applied math is called statistics and probability, where 3 come in section A and 3 in section B, and these are the topics. And the last part is numerical methods, where 2 come in section A and 2 in section B, and these are the topics. So what is ticked means the video is available on this platform, and at the end of this video there will be an end screen which will appear like this. So if you need a video, for example, in numerical methods, just double click on that. Video on mechanics, just double click on that. Or video on statistics and probability, you'll just double click on that. So what is half ticked means the video will be remade. So for example, this one will be remade. Now so far numerical methods is complete and statistics and probability is also complete. And in this video we are going to complete this part of kinematics with this video of resultant and relative motion. So before we start, I would like to wish you a happy new year of 2022. So we shall start our topic of resultant and relative motion. So this topic is divided into 2 parts. There is resultant motion and there is also relative motion. So both parts will be covered in this video. So let's start with resultant motion. Now resultant motion consists of mainly 2 parts. The first part is flying an aircraft. So an aircraft can be an airplane or helicopter. It also consists of steering a boat, or you can say a ship. So those are the 2 parts under resultant motion. And both parts, they have 2 parameters which are needed. One is the initial velocity, or the velocity in still air, that is if you are dealing with an aircraft, or velocity in still water if you are dealing with a ship or a boat. The other part is the velocity of wind if you are dealing with an aircraft, and velocity of current if you are dealing with a boat. So current is the flow of the river, for example, or water. Then here it can be wind or air when it comes to an aircraft. So these are the 2 parameters which are needed, and when you have these ones you can easily get the resultant velocity. So resultant motion is mainly about getting the resultant of these 2 velocities when it comes to an aircraft, and also getting the resultant of these 2 velocities when it comes to steering a boat. So let's start with steering a boat, and here we shall go to the topic of which we shall call crossing a river. Now when one is to cross a river from one point of the bank to another point of the bank, the effect of current or river flow has to be taken into consideration. Like we told you, there are 2 velocities. One is the initial velocity, or velocity in still water, and the other one is the velocity of the current. So this velocity of the current has to be taken into consideration. And there are 3 ways in which one can cross a river. For example, one can cross the river by the shortest route possible, or one can cross the river in the quickest time possible, or one can cross the river to a particular point on the other bank. Now these two look weird, they look as if they are the same, because if you cross the river by the shortest route and crossing the river in the quickest time, they look the same, but they are not the same, as we shall see in detail. So let's start with crossing the river by the shortest route. So when one wishes, know this word, wishes, to cross a river by the shortest route possible, it implies that he intends to reach to a point on the other bank directly opposite to his starting point. So these are the key words when you talk about crossing the river by the shortest route. One is that where he intends to go, he intends to to reach a point which is directly opposite. For example, we shall see the diagram, but the diagram here, these are the two banks, and if I'm here, it implies that if I'm to cross by the shortest route, I intend to reach directly here, directly opposite to my starting point. What does that mean? It means that he must therefore set his boat upstream at an angle theta to the bank such that the effect of the current enables him to reach that point. So here, what does the word upstream mean? Now if I'm here, if I'm standing here, for you to know where the upstream is or the downstream, I have to know the direction of the current. For example, we have two cases. One, the current can be, the river flow might be in that direction, or the river flow is in this direction. So for this case, if I'm standing here, I'll first draw a line through that point where I'm standing. Therefore, in this case, upstream means this side of this line, and downstream means this side of that line, of the left hand side. But for this case, if the river is flowing this direction, upstream means this side, and downstream will be this side. So that's what the word upstream and downstream means. Now here they told us he must set his boat upstream at an angle such that the effect of the current enables him to reach that point. Therefore, it means that if I'm here and I want to reach here, remember the river is moving in this direction, so if I just go straight, it implies that the effect of this current will push me away, and I will end up reaching somewhere where I don't want. What does that mean? It means that I have to move in this direction like this, such that this wind pushes me and I'll be able to reach where I intended to reach. So that's what they mean by crossing the river by the shortest route. Of course, theoretically it seems weird, but as we shall go through the questions, you will master the concept. So the resultant must be in the direction where he intends to reach. So in the question, they will always tell you where the person intends to reach, and that will be the direction of your resultant velocity. Like I told you, resultant motion deals with getting the resultant velocity. And because velocity is a vector quantity, you must get magnitude and direction. Now the direction is what we call the course. So the course set can be determined as follows. So let's see how the course can be obtained. Here we shall make an illustration first. So this will be the direction of the current or the river flow, and this river is D. The width of this river is D. These two are the banks of the river. Therefore, like I told you, where he intends to go is where the resultant velocity will be. So this is our resultant velocity because he intends to reach this point, which is directly opposite. So each time they talk about crossing the river by the shortest route, it implies that he intends to reach a point which is directly opposite the starting point. So point A is the starting point, and point B is his destination. And his destination must be directly opposite the starting point. That is what you always need to remember each time they talk about shortest route. Now from there, I will have to mind about the direction of the current. The current is in this direction. Like I told you, because it's in this direction, they told us you must go upstream. So I have to go in this direction such that this current pushes me up to my destination here. So let's do that. So this will be the direction of this velocity in still water, and the wind, effect of the wind will push him to his rightful destination. Now this diagram sometimes confuses students because, like I told you, the person has to reach here. Now the question is, why don't I extend this up to here so that it comes up to here where I intend to reach? Now the reason why we don't do that, it is because velocity velocity deals with direction, but distance deals with the actual position. Now this velocity will not show the actual position. Doesn't mean that he stops here. If this was distance and this was distance, it implies that this will be the actual position where he stopped. But this is just velocity. It shows you the direction. That is why we are not putting it here, and we are putting it within the current. Because if we extend it again here, someone may ask, how can the river flow along the bank margin, which will make it difficult to explain. So Vs is the velocity in still water, and Vc is the velocity of the current, and this theta is the cos they will always ask. So in this question they will ask for this cos, or costed by the boat, or they ask for the resultant velocity, or they ask for both, and also they can also ask for the time taken. Now let us look at how you can answer such a question. First of all, when they ask for cos, you realize that this is a right angle triangle. Therefore this angle is equal to this angle, the alternating. With this angle here, this will be the adjacent and this will be the hypotenuse, meaning I can use cos theta. Therefore cos theta will be equal to the adjacent divided by the hypotenuse. Now from there it implies that I can get my cos, and to be in this direction to the bank. That is one question they can ask. They will also ask for resultant velocity. So if they ask for resultant velocity, the good thing, this is the right angle triangle, so you can use Pythagoras theory. So remember, this is the hypotenuse, so by Pythagoras theory, this V will be equal to the square root of Vs squared minus Vc squared. Note that we are using minus here because this V is not the hypotenuse. If V was the hypotenuse, then we would have used the plus here. Another question they ask is the time taken to cross the river. Now time taken, remember we already know that time is equal to distance over speed. So in this case the distance used must be along the resultant velocity. So this is the resultant velocity, that is what we use as the speed, and the distance along the resultant velocity is what we use as the distance moved. So if our resultant velocity was here, as we shall see later in this video, it implies the distance used will be from here, you draw a straight line up to here, that will be the distance used. but we shall see that still in this video. So these are the 3 questions which they will always ask. So with that, let us go through some of the questions. Question 1 says, a stream is running at 3 kilometers per hour due east. If a man can row a boat in still water at a speed of 5 kilometers per hour, find the direction in which he must row in order to go straight across the stream in the northern direction. If the breadth of the river is 100 meters, find how long it takes him to cross. So how long means they want the time taken to cross. Then here direction means they want the course. So like we did, we shall first make an illustration. So in this case, they gave us that the width of the river is 100 meters, but because the speed is in kilometers per hour, it implies that even the distance has to be changed to kilometers. That is why you see here 0.1 kilometer. The next is, here they told you where he intends to go. It says that in order to go straight across the stream in the northern direction. So that is where your resultant velocity will be. So where you intend to go is where your resultant velocity will always be. Now from there, we shall realize that this will be the upstream because the river flow is in this direction. Therefore, we shall come and draw our velocity in still water in the upstream, which is here. Then from where this one stops, we shall add on the velocity of the current so that it will form our triangle across the triangle. So they ask for direction, meaning we have to get this angle. So this angle here is the same as this angle alternating. And now we have this adjacent and this hypotenuse, meaning that we shall use cos. Therefore, cos theta will be equal to the adjacent, which is 3, over hypotenuse, which is 5. And when I use a calculator, theta will be 53.13 degrees. Now in mechanics, we have been encouraging you to use 4 decimal places. But when it comes to the angle, the highest degree of accuracy must be 2 decimal places. So for angles, we use 2 decimal places. Elsewhere, we shall use 4 decimal places. So we can come and conclude that the boat must be steered at an angle of 53.13 degrees to the bank. That was this part, but they also asked for the breadth. Sorry, they also asked for how long it takes him to cross. Now, for how long, it means that we shall remember we use resultant velocity. So the first thing to do is to get our resultant velocity. So to be hypotenuse squared minus 3 squared. Square everything and a root to give you 4 kilometers per hour. Now that we have got the velocity and we know the width, the breadth, it implies that we can get the time. Remember, time will be, remember I told you the distance used must be in the direction of the resultant velocity. So the distance used will be distance AB, which is 0.1 kilometer. And the resultant speed, we have got it as 4. Therefore, 0.1 over 4 will give you 0.025 hours. And that's what they wanted. So that was question 1. Now we shall go to question 2. So question 2 says, 2 points A and B on the banks of a river are directly opposite. A boy capable of swimming at 1 whole number 7/18 meters per second in still water wishes, know this word, wishes, to swim directly from A to B. Given that the river is flowing at a rate of 5/6 meters per second. Determine Roman 1 the boy's speed along AB, and Roman 2 the width of the river if it takes 2 minutes to cross the river. So still here we shall need a sketch. So we shall now locate points A and point B. They are directly opposite each other. Now where he intends to go, note this word, wishes to swim directly from A to B. So where he intends to go is where the resultant velocity is placed. Then because the river is flowing in this direction, it implies that upstream is this side. Therefore we shall come and draw our velocity in still water upstream. Then from there we shall add on the velocity of the current to close our triangle. Okay, now part A, they ask for the boy's speed along AB, so they want the value of this resultant velocity. Now speed means magnitude. Therefore Roman 1 shall say by Pythagoras theory we shall come up with this as our speed, because they only wanted magnitude, they didn't want direction. Then for Roman 2 they said find the width of the river if it takes 2 minutes to cross the river. Now we already know that time taken is equal to distance over speed. Now here distance used will be this one because it is in the direction of the resultant velocity. Therefore we shall say that time taken will be equal to d over v. Therefore when I make d the subject, it will be v times t, and v is here, and time we have got it as 2 minutes, but 2 minutes have to be changed to seconds because our velocity is in meters per second. When you do that, you'll come up with 400/3 meters, and that will be the width of the river. So that has been part A. Now we shall go to the second part of crossing a river in the quickest time possible. So part A was about shortest route. Now here we want to cross the river in the quickest time possible. So when one wishes to cross a river in the quickest time, the course set will be directly across the river. Remember, for shortest route the course set was upstream, but when it comes to the quickest time, the course set must be directly across the river. The current will then carry the boat downstream. What does that mean? It means that I'll set my boat in this direction, but remember there will be the effect of the current. Therefore I'll end up reaching somewhere else where I don't want to reach. That is why they call it quickest time, and the other one was shortest route because you exactly reach your intended place. But in quickest time you only mind about reaching the other side of the bank. So let us also illustrate that. So in this case here we shall not put there the resultant velocity, we shall put the velocity in still water. Now where it stops we shall add on the velocity of the current. Now from here, from start to end, that will be your resultant velocity. So let's do that. Okay, so this is why they told you that the current will then carry the boat downstream. So this is the distance. D1 is called distance downstream, and D2 is called the width of the river. Vc is the velocity of current, Vs velocity in still water, v is the resultant velocity and theta is the course or the direction of the resultant velocity. So they also ask for this direction, theta. So theta, this angle is the same as this angle, and now we have this adjacent and the opposite, meaning we shall use tan. So tan theta will be equal to the adjacent, which will be equal to opposite. Remember, tan is opposite over adjacent. So opposite, which is Vs, divided by the adjacent, which is Vc. That is if you are using velocity, but still you can also use distances, because this angle will be the same as this angle. So if I use distance, it implies that the opposite will be this d2 and the adjacent will be this d1. That is why you see here d2 over d1. So here this one is also a principle called similarity. I think you remember that in your O-level, similar triangles. So now that means that when I make theta the subject, I'll be able to get the direction of this resultant velocity to the bank. They can also ask for this resultant velocity. So this is the hypotenuse. I think realize that now we are putting plus, because this v is the hypotenuse. Therefore, by Pythagoras theory, v will be equal to the square root of vs squared plus vc squared. Then the distance AB, now this distance AB, remember, for you to get the time taken, the distance used must be along the resultant velocity. That is why you have to first get distance AB before you get the time taken. So AB, we already know this and we know this. Therefore, by Pythagoras theory, this distance AB will be d1 squared plus d2 squared, everything under square root. After getting AB and getting V, you can get your quickest time taken to cross the river, and to be equal to D over V. So you must be keen to realize that the distance must be along the resultant velocity. So that we shall go through these questions. Question 1 says, a boat can travel at 6 kilometers per hour in still water. A river is 250 meters wide and the current flows at 4 kilometers per hour. Calculate the shortest time taken. Know this word, shortest time taken, to cross the river and the distance downstream that the boat is carried. So to cross the river in the shortest time, you must remember that the course set is directly across the river. Therefore, we shall come and draw our sketch. So this is where we shall set our course. So this is where the velocity in still water will be. Then we shall add on the velocity of the current, which is 4 kilometers per hour. Now from start to end, that will give you your resultant velocity. Now this D is what we call the distance downstream, and that's what they want. So by similarity, you can, when you get D over 0.25 is equal to 4 over 6. So let's see that similarity. So by similarity, D, if I use this angle, this will be the adjacent and this will be the opposite. is equal to 4 adjacent over opposite, which is 6. So we have to be keen to give values which correspond. So this d is the adjacent of distance, and this is the adjacent of velocity, and this is the opposite of velocity, this is the opposite of distance. So they should rhyme. This d will go, this d corresponds, if this d is the numerator, even here 4 will be the numerator, and if 0.5 is the denominator, 6 must be the denominator. Now from there, my aim is to make d the subject. So when I make d the subject, d will be 0.1667 kilometers, and that will be the distance downstream they wanted. Then from there we shall now go and get our velocity. Here they said find the shortest time taken. For you to get the shortest time, remember shortest time is got by saying distance, and the distance we're going to use will be distance along this v, so it will be distance AB. It will be distance over velocity, so we have to get this value of v and also the value of AB. Therefore here I'll get the value of v, it will be 7.2111 kilometers per hour. What about the value of AB? AB by Pythagoras theory, it will be this, which is 0.3005 kilometers. Now that I've got distance and velocity, I can get the quickest time taken to cross the river, and it will be 0.0417 hours. So now we shall go to crossing a river to a particular point on the other bank. So in order to cross the river and reach a point set B on the other bank upstream, the course set must be in such a direction that the resultant velocity of the boat is in the direction AB. Remember we said where he intends to go is where the resultant velocity will always be where he intends to go. Therefore now this one is somewhat similar to the one we covered in part A, crossing by the shortest route. The only difference is that the one for part A, it is the must. He must reach a point exactly opposite the starting point. But in this case, it implies that it's not a matter that he will always reach a point which is directly opposite the starting point. For example, you may reach a point, for example, B here. So that is where this part C comes in. Otherwise, the procedure would have been the same as the one in part A. So for example, in this case, he intends to reach this point B. That is why the resultant velocity is now here and no longer on this vertical. If it was part A, it should have been on this vertical, because for part A, or crossing by the shortest route, it is a must for him to reach a point exactly opposite his starting point. If it is not, then the question lies under part C, which we are on now. So this D1 is what we call the distance upstream, and this D2 is what we call the width of the river, and this will be the resultant velocity of the boat. So we shall take our velocity in still water upstream beyond this line AB. Why? Because even this one, it will be upstream because it is beyond this vertical line. But if you take this direction here, the current will blow you this side. That means that you will not be able to reach this point B. Therefore, that is why we take it beyond this line AB, such that the wind can blow you, the current can blow you to reach where you intend to reach. So from here now, we remember we start from known to unknown. Now for this alpha, I have this opposite and this adjacent, therefore I can get my tan alpha, after which I can get alpha. After getting alpha, I can get theta 3 because this alpha is the same as this angle here, alternating angles, and these two are angles on a straight line, therefore they add up to 180. Now when I make theta 3 the subject, I'll come up with 180 minus alpha. Now my aim is to get this theta 1. So now that I have this, I know this, and I know this, it means I can use sine rule using this and this. Therefore the next angle to get will be theta 2. So I'll come here and say that by sine rule, sine theta 2 over Vc is equal to sine theta 3 over Vs. Now from this it means I can get my theta 2, and after getting theta 2, which is this, I will remember that this angle is alternating to this angle. Therefore alpha is equal to theta 1 plus theta 2. Now when I make theta 1 the subject, theta 1 will be equal to alpha minus theta 2, and that will be the cos set by this to the bank. When I use cosine rule, I can get out my resultant velocity by saying v is equal to square root of vs squared plus vc squared minus 2 times vs vc cos theta 1. I also need to get the distance AB, which is along the resultant velocity, and it will be d1 squared plus d2 squared, everything under root. Now that I have the velocity and the distance, I can get the time taken to cross the river, and it will be d over v. So with that, we shall go through these questions. Question 1 says, a boat crosses a river 35 meters wide, flowing at 4 meters per second. To reach a point on the opposite bank 50 meters upstream. The boat's speed in still water is 12 meters per second. Find the direction in which the boat must be headed. So still here we shall need a diagram. So he intends to reach a point 50 meters upstream. So from here I have to measure off 50 meters, and that is where he intends to reach. So I shall come and show it. So this will be the 50 meters, and the river was 35 meters wide, and where he intends to go is where the resultant velocity must be. Then I'll come and put my distance, my velocity upstream in still water, and then add on the velocity of the current to form a closed triangle. Then from there, still go through the procedure we have seen in the previous slide. Using tan, it will be 35 over 50, therefore alpha is 34.99. So in mechanics, we usually tell you to use 4 decimal places, but when it comes to angles, the highest degree of accuracy of an angle is 2 decimal places. Now after getting alpha, I can get theta by saying 180 minus alpha to get 145.01. Then from there I can use sine rule to get the value of theta 2, and theta 2 will be equal to 11.02. After that I will be able to get my direction of theta 1, which is 23.97. So I'll conclude that the boat must be headed at an angle of 23.97 degrees to the bank. So what we have dealt with in part A, part B, and part C has been called geometrical approach. Now geometrical means you use a diagram, velocity diagram. Now vector approach, the difference that now we use these tildes, but the symbols will always be the same. For example, Vs tilde will note the velocity vector of the velocity in still water, and vc tilde will denote the velocity of the vector of the velocity of the current, and v tilde will denote the vector of the resultant velocity. Now another word for word resultant is called actual. Therefore the formula, after getting them in vector form, you can use this formula that resultant velocity is equal to velocity of the velocity in still water plus velocity of current. But you must be keen to first change these ones to be in vector form, otherwise the formula will not work. So with that, we shall go through these questions. Question 1 says, a boat is drifting in the sea where the velocity in still water is 2I3J. The velocity of the current is I-5J. What is the resultant velocity of the boat? So Vs, or the velocity in still water, is that, and the velocity of the current is that. Therefore the resultant velocity will be got by adding the 2 to give you 3 negative 2, and that would be that is what they wanted. Then question 2 says, a ship is traveling at 10 meters per second in a direction 4I minus 3J in a wind with velocity this. What is the speed of the ship in water? So first of all, they have given us the magnitude of the resultant velocity and the direction. Therefore we have to first convert it to vector. Now to convert it to vector, you have to first get the magnitude of the direction vector, which will be 5. Therefore I'll use the formula. This formula was already covered under motion in a Cartesian plane under kinematics. So if you have not covered with it, it's advisable that you first watch that video. So the velocity vector is equal to the magnitude of that velocity divided by the magnitude of the direction, everything multiplied by the direction vector. So in the end, we shall come up with this as our resultant velocity. Now that you have got that, we shall code the formula and then substitute resultant velocity, velocity of the wind. So we are left with this as the only unknown. And when I make it the subject, I'll come up with 1 negative 5 as the velocity. But the question asked for speed, so speed means magnitude. Therefore, come and get the magnitude of the velocity in still water, and that is what they wanted. So that has been steering a boat. Remember, resultant motion is divided into 2 parts. The first part is steering a boat, and the second part is flying an aircraft. So now we shall go to the second part, which is flying an aircraft. So suppose an aircraft flies from point A to another point B with a velocity Vs, which is the velocity in still air as shown in figure A. So they will always give you the velocity in still air and its direction. And wind is blowing with a velocity Vw in the direction as shown in figure B. Still, they will also give you the velocity of the wind and its direction. The resultant velocity of the aircraft can be got by combining the 2 velocities to form a closed velocity diagram as shown in figure C. So when they give you these 2 velocities with their direction, it implies that you can draw you a closed velocity diagram. So the procedure is still the same. Start with this one as it is. Where it stops, add on this one as you can see it here. Then to stop here. Now the line joining from the starting point to the end point is what will have our resultant velocity. That is why you see resultant velocity there. So basically that is how they draw a closed velocity diagram under this part of flying an aircraft. Now next is to use that diagram. So by geometry, the magnitude and direction of the resultant velocity V can be got using either cosine rule or sine rule. So if I use cosine rule, I will be able to get the magnitude. of the resultant velocity. And if I use sine rule, I'll be able to get the direction. So sine rule and cosine rule were covered under trigonometry. So if you are not conversant with them, I advise you to first watch the video of trigonometry under math paper 1. Now after getting this theta, I'll come here and remember that my direction from here, it will be up to here. That is why therefore I'll get up. So the direction is this plus this to the horizontal. So there are many ways of stating the direction. It can mean in terms of compass direction. For example, north this degrees east, or north this degrees west, like that, as we shall see along with the questions. So that is geometry. But now the good thing is that such questions of flying an aircraft, they can be approached in any of the two ways. The first is geometrical method, where you have to draw a closed velocity diagram. Then the second part is called the vector method, where you have to first change the velocities in vector form, because they will usually give you the magnitude and direction, so you have to change them in vector form, as you shall see. So we shall look at both methods in the examples, but should be reminded that in an exam you have to choose one method. Now the good thing is that they will not specify which method to use. It is you to choose which method is easier and go with that. So we shall start with question 1. Question 1 says, an aeroplane has an airspeed of 200 kilometers per hour and flies on a course of north 60 degrees east. So like I told you, they will always give you the magnitude and direction. A wind is blowing steadily at 50 kilometers per hour from, not this word, from the northwest. Find the track and the ground speed of the plane. So track will be direction and ground speed will be the magnitude of the velocity of the plane. And that is, and in particular they mean the resultant speed. So we shall look at both methods. So let's start with method 1. Now for method 1, you have to first sketch the magnitude and direction. So for aeroplane, magnitude is 200 and the direction was north 60 degrees east, which is here. So the velocity of the aeroplane, let it be VA. What about the one for the wind? The one for the wind, they said 50 kilometers per hour from northwest. Now this word from, what does it mean? Now from means the arrow points towards this center. Here they just said flies on a course, this. So it just points, the arrow goes away from this point. But when they say from, it is coming towards. That is what you should always remember. Now northwest, the angle is always 45. They don't need to tell you that's 45. Now from there we shall have to draw our closed velocity diagram. So closed velocity diagram, we begin with this one, which is here. Then where it stops here. So from this point we shall add on this, which is that one. Okay, now the resultant is drawn by joining a line. Remember, we are using rulers to draw these diagrams. So mechanics, you must have a ruler. Now you are going to get your ruler and join from here up to here, a straight line, and that will be your resultant velocity. So let's do that. So this is the resultant velocity which they want here. Then the track means you have to first get this angle theta. Then you can add it to this to get our north, this degrees east. Now here, this angle is this angle here, and it is alternating with this. That is why you're seeing 45 there. Then this one is this angle here, and it is alternating with this. That's why you're seeing that angle there. Now the reason why we are doing that, it is because in your closed triangle you must look for a way of getting at least one known angle. It can be this or this or this, depending on the question. So in this case it is this one which is easy to get. If you don't get any angle inside the triangle, there is no way you can proceed, because both sine rule and cosine rule will require you to have at least one angle, since you don't know the resultant velocity. So now let's use sine and cosine rule to get what they want. So if I use cosine rule, I'll come up with this. Remember, when you go here, by cosine rule, this one faces this angle, so the whole of this is 105. Therefore v squared will be equal to this squared plus this squared minus 2 times 200 times 50 times cos 105. Therefore to get v you have to get the square root. That is why you are seeing this square root there. So we are using 4 decimal places. Then you shall also use sine rule to get the value of theta. So by sine rule, if you go here, by sine rule, I know this and this, and I want to get this, meaning I'll use this velocity. Therefore, it implies that sine theta over 50 is equal to sine 105 over v, which v we have already calculated. So with that, I'll come up with the value of theta as 12.78. Therefore, the direction is north, 60 plus 12.78 degrees east. And it comes from here. I'm measuring now in terms of compass direction, so I'll measure from north going up to here, which is 60 plus theta. And we have already got theta, therefore we shall add the 2 to get the required direction. So the track is this and the ground speed is that. Now that was method 1. Like I told you, there are 2 methods. You can either use geometrical approach or vector approach. So vector approach, still you need to make some small sketch which will help you to convert the magnitude and direction in terms of into vector. So the direction, magnitude and direction of the velocity of the aeroplane is that. Therefore, by resolving, remember we were given 60 but we are getting this 30 because most students are used to resolving when given the angle to the horizontal. So the angle to the horizontal is 30, meaning that always the upper part will be cos that angle and the lower part will be sine that angle. This tilde is very, very vital. Then also we shall sketch the velocity of wind, and then also get its vector. So remember vector, this one, it implies that the horizontal is going this direction to the right, which is positive, but vertical it is going downwards, which is negative. That is why we are seeing negative here. So now that I have got them in vector form, I can go and quote the formula. Therefore, resultant velocity is equal to velocity in still air plus velocity of wind. So velocity in still air is that, velocity of wind is that. Then when I add the two, I'll come up with this. So remember to use 4 decimal places here. So remember they want magnitude and direction. So magnitude of this will be this squared plus this squared, everything under square root to give you this, which is similar to the one before. What about direction? Direction, both are positive. Positive horizontal means you go to the right, and positive vertical means you move upwards. Then from start to end gives you your resultant velocity. So I want to get my direction in terms of compass direction. That is why I'm putting my theta here, and alternating angles, it gives you this. It is the same as that. Therefore, with this angle we have opposite and adjacent, meaning you can use tan, and theta would be 72.78. Then question 2 says an aircraft has to fly from airport A to another airport B, which is 240 kilometers from A, on a bearing of 120 degrees from A. A wind with speed of 15 kilometers per hour is blowing due north. Note this word, due north, throughout the flight. If the speed of the plane in still air is 300 kilometers per hour, find Roman 1, the direction in which the plane should steer. Roman 2, the time for the flight. So still there are two methods, geometrical or vector. So let's start with geometrical. Geometrical, we shall first make some sketches. So in this case, we have to locate first of all the positions. If you look at this, they said 240 kilometers from A on a bearing of 120 degrees from A. So it means that when I stand at A, I have to measure a bearing of 120 to locate the position of B. Okay, so the whole of this is 120, but this alone is 90, meaning the remainder will be 120 minus 90, which is 30. So that explains why you are seeing 30 there. Then by alternating angles, this angle is the same as this angle. Okay, that is initial position. Then next we shall go to the velocity whose direction is known. Now if I look at this, they said a wind with speed this is blowing due north throughout the flight. So first of all, the velocity is where the initial positions are. Remember, because this aircraft is flying from A to B, so where you intend to go is where the resultant velocity must be placed. He intends to move from A to B, that is why the direction is in that order. Okay, then from there, now here I don't know the direction in still air. So what I'm going to do, I'm going to start with the direction of the current, or the direction of the wind. The direction of the wind is 15, okay, the magnitude is 15 and is blowing due north. So it is going to meet this point like that. So this is the direction of your wind, is blowing due north at 15 kilometers per hour. Therefore, the direction of the direction in still air is automatic, because you have to join from here up to here. When I join, I'll come up with this. Now what we are doing, it may be confusing, but we are trying to go in the reverse way. Remember previously we used to start with the velocity in still air followed by the velocity of the current, but now here we are given the direction of this current of the wind, but we don't know the direction of this in still air. That is why you have to first begin with this, which is towards the end. So now that we have drawn our closed velocity diagram, we can answer the question. So for Roman 1, they ask for direction in which the plane should be steered. So they want this value. You have to get the direction, you must first get this value of theta. So by sine rule, we can get theta as 2.48. So let's see how it comes about. So sine rule, this angle is 120, it corresponds to this, and this angle corresponds to this. Therefore, sine theta over 15 is equal to sine 120 over 300. So that is where this came from, and when I make theta the subject, I'll come up with this to 2 decimal places. Therefore, the bearing is 90 plus 30 plus 2.48, which is 122.48. So let's see where it comes from. So bearing has to be measured from north up to here. First of all, this alone is 90, this is 30, and this is theta. So we have to add all those three. So we can conclude, and then we go to Roman 2. Now for Roman 2, they ask the time for the flight. Now time, just like it was under crossing a river, the distance used must be the distance along the resultant velocity. And the good thing, the distance was given as 240 kilometers. Now that means that when you get this v, you can get the time using that v and this distance. Therefore, let's go and get our v. So first of all, beta is equal to 57.4.52. Therefore, by sine rule still, v over this is equal to this over that, to give you v, the value of velocity, as that. Therefore, time is distance AB over speed along AB. Distance was this and speed is this. When I divide the two, I'll come up with this as the time of flight. Now that has been geometrical approach. What about vector method? Now vector method still, you have to first make the simple sketches of the magnitude and direction, which will help you to get the vector form. So in this case, like they told you, he intends to move from airport A to airport B, meaning that this will be the direction, this is where the resultant velocity will be. Remember, resultant velocity is always placed where he intends to go. So he intends to move from A to B, that is why we are putting our velocity there. Therefore, that means that if x is the magnitude of the velocity, then the vector form, it will be x cos 30 x cos 30 then negative x sine 30. Why? Because from here to here, horizontally you are moving to the left, which to the right, which is positive, but vertically you are moving downwards, which is negative. That is why you see a negative x there. Now you can choose to simplify this, because this is a particular angle, and therefore it becomes 0.5 x root 3, and this one becomes negative 0.5x. Then when it comes to the wind, he moves due north direction, which is that. Therefore, in vector form, it will be 0.15. They also gave us the magnitude, which is this, the magnitude of the plane in still air. Therefore, now that we have got these in vector form, we can come and quote our formula that resultant velocity is equal to velocity in still air plus velocity of the wind. When I substitute, I'll come up with that and make VP the subject. It will be that. Okay, but the good thing, I know that the magnitude is 300. Therefore, come and get the magnitude of this. So this squared plus this squared, everything under square root, and I will equate it to 300. Then put square on both sides and expand. This gives you this. Then this one expanding gives you this, and square this gives you this. I think we realize that we have only one unknown. So now this is the quadratic equation in x. Therefore, I'll use bulldozer method to get the values of x. So now, use a calculator, I'll come up with two values, and those will be this and this. But we shall eliminate one, so we shall say x cannot be negative, therefore x is this, based on what is given. Because if you look at this, it implies that this x has to be a positive because it is a magnitude. Now, after getting that, it means that the actual speed v is equal to this. Remember, in the question they wanted the direction in which the plane should steer and the time of flight. So now I've got the actual speed, or the resultant speed. Therefore, I can proceed to get my time and direction. So first of all, VP, remember VP was given in this way, so when I substitute for x, I'll come up with this, and with this I can be able to get the direction of this, or the direction of this velocity in still air. So this is positive horizontal and negative vertical. So positive horizontal is to the right, negative vertical is downwards. Therefore, the resultant will be in this form. For you to get the direction, I have to get the value of theta here. So tan theta will be equal to opposite over adjacent, which is this. Therefore, theta will be equal to 32.48 degrees. Now from there, I can get my bearing, because bearing is from this up to here. That is why I'm saying 90 plus 32.48, which gives you 122.48 as before. So basically that is how they use vector method to get the direction. But they also wanted time. So for you to get time is distance AB over speed along AB. Now speed along AB is the speed of the resultant, which is this. And the distance is the distance apart, which was given in the question as 240. So when I divide the two, I'll come up with this as the time of flight. So whether you use vector approach or geometrical approach, you will still get the same answers and same marks will be awarded. So most students, because they see geometrical approach is shorter, they may think that when they use vector they will get more marks, but no, you'll all get the same marks. So question 3 says a helicopter leaves an airfield A to fly to another airfield B 500 kilometers away on a bearing of 140 degrees. There is a steady wind of 30 kilometers per hour from northeast. Note this word from. The helicopter has an airspeed of 150 kilometers per hour. So the velocity in still air is this. Part A, find the course the pilot must take and the time for him to reach B. Then part B, what course should be taken for the return journey if the wind continues as before. So just start with the part A. So we have to make a simple sketch. So for geometrical method, we shall first locate the initial positions of A and B. Remember they told us that A, let me see the positions, helicopter A leaves airfield A to another airfield B 500 kilometers away on a bearing of 140. Okay, so when you come here, bearing of 140, it means that from here up to here is 140. What does that mean? It means that this remaining part to make 180 degrees will be 40. Now because this is alternating to this, that is why you are seeing 40 here. Then we shall come and put our resultant velocity along that line. Now we're using V1 because in the same question you also have a return journey. So V1 will denote forward and V2 will denote return or backward velocity. So next is to show the 30 kilometers per hour. So 30 kilometers per hour, if you come here, they said, now here because we don't know the direction of this airspeed, that is why we begin with the velocity of the wind. So they said from northeast. From means it is coming towards the center. So northeast, yeah, it is coming towards in that direction. So that is why you are seeing here that is coming this direction, and northeast means this angle is 45. Now when I join from starting point from here up to here, I'll be able to get the airspeed, the direction of the airspeed, which is the magnitude is 150. Now here I've succeeded, I've been able to get one angle inside the triangle. So like I told you, the first thing to do is to ensure that you get at least one angle inside the triangle, because without that one angle you cannot proceed. So now that we have that angle, we can proceed. So you say by sine rule, sine theta over 30 is equal to sine 85 over 150, which is here. Therefore theta will be 11.49. So after getting theta, I'll come and get my beta, because this 40 here is the angle here, meaning that this remaining part to make 90 will be 50. That means that theta plus beta is equal to 50. Therefore when I make beta the subject, it will be 50 minus theta, which is 11.49, to give you beta as 38.51. So after getting beta, I can get the bearing of the airspeed, which is from here to here, which is 90, plus this beta, which is that, and it gives you 128.51. Okay, so that is the course which the pilot was supposed to take. They also want the time taken for him to reach B. So the time taken, for you to get the time, you must get this resultant velocity. So to get it, I'll have to first get this alpha so that I can use sine rule or cosine rule, any of the two. So alpha, how do we get alpha? We shall remember that these are angles of a triangle add up to 180. So 85 plus theta, which is 11.49, plus alpha will add up to 180. Therefore make alpha the subject, it gives you 83.51. Then from there I can now use sine rule or cosine rule. So sine rule, V1 over sine alpha, which is this, is equal to 150 over sine 85, which is this. Therefore when I make V1 the subject, V1 will be this. So now I've got the velocity and I also know the distance. Therefore time taken will be distance AB over speed along AB, which gives you 3.3421 hours. Now that has been part A. Now part B said, what course should be set for the return journey if the wind continues as before. So the diagram will be somewhat similar, but we have to reverse the direction of the resultant speed. So that means that now it will be pointing in this direction from B to A. The direction of the wind did not change, therefore it will be still from northeast. Then we shall join from here to here to get our airspeed. Now I've succeeded also to get an angle inside the triangle, therefore I can proceed. So sine rule, sine alpha over 30 is equal to sine 95 over 150 to give you alpha as 11.49. Then beta, this and this will be equal to 40, which is here. Therefore beta will be equal to 40 minus that to give you 28.51. Therefore the bearing will be that. Therefore the course the pilot must take is 331.49. And that's what they wanted. So I can also use vector approach. So vector approach, I'll come and still make some simple sketches which will help me to get the vectors of the resultant velocity and that of the wind. So from there I'll come and get this vector. Because I don't know the magnitude, I'll first let the magnitude be equal to x. Therefore the velocity of v1 will be that. So I also have to make a simple sketch for the velocity of the wind. Out of that I'll also get its vector. So I have the vector for v1 and also the vector for vw. And I remember the magnitude of this velocity of airspeed, or let me say the velocity in still air is 150. Therefore come and code the formula that resultant velocity is equal to velocity in still air plus velocity of the wind. Then I'll substitute and make VH the subject, or the velocity in still air the subject. Now from here I remember that the magnitude of the airspeed, or the velocity in still air, is 150 kilometers per hour. Therefore I'll come here and recall that, then I can substitute. So magnitude of VH is this square plus this square, everything under square root. Then put square root on both sides and expand. This gives you this. Expand this, I'll come up with this. Then square root of this gives you this. So next is to collect like terms. So this is x, this one has x squared and this one has x squared. So pull out x squared to remain with cos squared 50 plus sin squared 50. Then also we are done with this and this. Then also this one has x and this one has x. So pull out the 30x root 2 to remain with cos 50 minus sin 50. Then this plus this gives you 900, and this one remains untampered. So now I have a quadratic in x, therefore I can use bulldozer method to get the values of x. But I have to eliminate 1, therefore I'll come and say that the negative is eliminated. I remain with the positive 1 alone, because it was magnitude. Magnitude can never be negative. Therefore the actual speed of the helicopter will be this. and time taken will be distance AB over speed along AB, which is given by that, and you come up with this as before. Then from VH, which is equal to this, substitute for X, you come up with this, and with that I can be able to get the direction of the velocity in still air. So this is positive horizontal, negative vertical. I can use tan theta to come up with theta as this. Therefore the bearing will be 90 plus theta, which is this, as before. That was part A. What about part B? So for part B, they said what course should be taken for the return journey if the wind continues as before. So here still we shall need to make a sketch and reverse the velocity of the resultant. So here we have reversed the velocity of the resultant. Therefore, shall let y, because we already used x in part A, so shall use another letter which is y. In vector form of this, it will be this when I resolve. What about for the wind? It remained constant from northeast. Therefore, its vector, it will be the same. Then I remember that the magnitude of the airspeed is that. Now I'll come and quote the formula that resultant velocity is equal to velocity in still air plus velocity of the wind. Then I'll substitute V2, VW, and remain with VH. So VH, make it the subject, you'll come up with this. But remember that VH magnitude is 150. Therefore, I'll come here and recall that this is equal to this. Therefore, substitute this square plus this square, everything at a square root equal to 150. Then square both sides. Then collect like terms, and then simplify. To get a quadratic, use bulldozer method to get the values of y. Then you have to choose, you have to eliminate 1. Remember, magnitude can never be negative. Therefore, y will be equal to the positive part. That implies that the actual speed of the helicopter is this. Time taken will be distance AB over speed along AB, and it gives you 3.4631. Then for the direction, VH substitute for y and come up with this vector, that vector for airspeed. Therefore, negative horizontal, positive vertical, negative horizontal, positive vertical. So tan theta will be equal to that, implying that theta is that. Therefore, the bearing will be from here to here is 360 minus theta, which is 331.49, and it's the same as before. So now those have been the two parts of resultant motion. Now from this part onwards, up to the end of the video, it will be now relative motion. So the first part of relative motion will be relative velocity. Now what is relative velocity? This is the velocity with which a body moves as observed from another body. For example, if there are two cars and someone stands at, I have car A and car B, then someone is in car B and watches car A moving. Now the velocity which car A will appear to be moving as seen by this observer in car B is what we call the relative velocity, and in particular it will be the velocity of A relative to B. Now relative means that where are you? So relative to B means that you are positioned at B and we are seeing body A. So we shall consider two vessels A and B which are in motion, where each is moving with a specified direction. The velocity with which A appears to move as observed by an observer in vessel B will be different from its actual velocity. Note this word appears and this word actual, and it's referred to as the relative velocity of A to B, velocity of A as it appears to an observer at B. Therefore, if VA is the velocity vector or is the actual velocity of A in vector form, and VB is the actual velocity of B in vector form, the relative velocity of A to B is denoted as in this way. So we start with A followed by B. That is how they write relative velocity of A to B. Now how do we expand this? To expand it, we shall look at what is starting here is what also starts here, and what ends is what ends here. So velocity of A relative to B in vector form is equal to velocity of A minus velocity of B. What you should note here is that these are vectors. That is why you are seeing those tildes. If it is not vector, there is no way you can subtract. We use geometrical approach. So here what we need to realize is that velocity of A relative to B and velocity of B relative to A, they are totally different. For example, if I want velocity of B relative to A, I will say velocity of B minus velocity of A. So with that, we shall go through these questions. Question 1 said, the velocities of two ships P and Q are I plus 6j and negative I plus 3j kilometers per hour respectively. So this is for P and this is for Q. Find the relative velocity of P to Q. So relative velocity of P to Q means that we start with P followed by Q, and to be Vp minus Vq. So I know Vp and I also know Vq, so when I subtract I'll come up with 2,3 as my relative velocity. Then question 2 said the velocities of two ships P and Q are j plus k and 2i plus j plus 2k respectively. Find the relative velocity of ship Q to P. So it means that we start with Q followed by P. Now here it was somewhat tricky because there is no I. That is why you put 0 here. Then you come and substitute Vq minus Vp to give you this as the relative velocity they wanted. So that has been vector approach for relative velocity. What about geometrical approach? Now geometrical, it takes some steps. So let's come here and say that suppose that the directions of VA and VB are shown in figure A and figure B. So this is one vector. Usually the question, they will give you magnitude and direction of each velocity. So this is the magnitude of velocity A and this is its direction, magnitude of velocity B and this is its direction. Now given these two, you are going to first look at the velocity, relative velocity they want. This is velocity A relative to B, and vectorially it would have been velocity VA minus VB. So minus VB means you are geometrically you are going to reverse velocity of B. That is why you see here minus VB. Now how do we get it? You get this same velocity with its direction, but you just reverse it. So it was going in this direction, it changes to go in an opposite direction. So that is how they get the minus VB. It means that you reverse the velocity. Now, how do we know what to reverse? We know what to reverse from here because this one is the same as VA minus VB. Now this minus VB is what tells you what to reverse. Now after reversing, what next? After reversing, we are interested now in this positive VA and negative VB. So we are going to come and first draw positive VA, and where positive VA stops, we are going to draw negative VB, because that is what we are interested in, VA minus VB. Now after drawing that negative minus VB, you get your ruler and join from starting point to end point with a straight line, and that will be the direction of your relative velocity. It should be noted that the diagram will be different if they interchange. For example, if they want VB velocity of B relative to A, it implies that it is this velocity of A which you are going to reverse. So those two are different. You must be keen to know to first realize or identify which relative velocity is needed. Okay, so let us make some notes on this diagram. So you are coming and say that to draw a vector diagram of velocity of A relative to B, the following steps are taken. The first step is to reverse the velocity of B, which is VB. Then step 2, draw the velocity of A, where it stops, add on the reversed velocity of B, which is negative VB. That is step 2. Then step 3, draw a straight line from the tail of VA, tail means where it starts from, up to the head of VB, where it ended. Then step 4, this line represents velocity of A relative to B, and this arrow placed, the arrow is placed on this line must be in the direction followed while drawing it. I think you have already explained it here, that when I'm drawing this line, I'm starting from here and stopping here. That is why the arrow is in this direction. Now by geometry, theta 1 is equal to 180 minus alpha plus beta. So theta 1, let's see, theta 1, this is theta 1 and this is alpha, this is beta. They are lying on a straight line, so when add all of them we must get 180. Then from cosine rule I can get the relative velocity using cosine rule. I believe by now you know how cosine rule works. So this squared is equal to this squared plus this squared minus 2 times VA times this cos theta 1. Now that negative is to show you that you have reversed, but when you are substituting you don't include it there. Then what about sine rule? Sine rule, I'll say sine theta 2 over VB is equal to sine theta 1 over VA relative to B, and from there I can be able to get the result, the direction of the resultant, which will be equal to theta 2 minus alpha below the horizontal. So this is what I already told you, that geometrically the negative sign on VB only shows that the direction of B was reversed, and therefore the negative sign must not appear in the calculations. So we shall see that as we are working out some examples. So question 3, we shall say a cruiser is moving at 30 meters per second in a direction of north 60 degrees east, and a battleship is moving at 20 meters per second in a direction north 20 degrees west. What is the velocity of the cruiser relative to the battleship? So still here there are two methods, geometrical and vector. We shall look at both of them. So let's first begin with geometrical. Like we told you, you have to first make sketches of the magnitude and direction. So this is the velocity of the cruiser, and the direction is north 60 degrees east. For the battleship it is north 20 degrees west, and it was 20 meters per second. Now here we have reversed it. Why? It is because the question said the velocity of the cruiser relative to battleship, that is V-C relative to B, meaning that we are interested in VC and negative VB. So when I reverse this, I'll come up with this. Okay, now from there I have to draw a sketch, a complete velocity diagram. So the first thing to do here, I'll come and get this velocity and put it there as it is. Then where it stops, I'm adding on the negative or the reversed velocity. I'm not interested in the positive velocity here. I'm interested in the reversed velocity. So at this point, I'm going to add on the reversed velocity. And like we said, the negative shows the direction. That is why now here in the calculation, I'm putting there a positive. Now a line from start to end will show your relative velocity. So with that, we have drawn our diagram and also managed to get an angle inside the triangle. Therefore, we can use the diagram to answer the question. The question wants, what is the velocity of the cruiser relative to the battleship? I know this, I know this, I know this. That means I can use cosine rule. So by cosine rule, I come up with the relative velocity as that. What about by sine rule? By sine rule, theta will be that, and therefore the bearing will be 96.59. So if you come here, the bearing will be from here up to here. So 60 plus theta gives you the bearing. And that's what they wanted. When they say velocity, they want magnitude and direction. Okay, so now we shall go to method 2. Method 2 still, we still need to make those simple sketches first for both velocities. But this time, we are interested in the angle to the horizontal because that's what most students are used to when resolving. Therefore, VC will be 30 cos 30, then 30 sin 30. What about for the battleship? Still, we are interested in the angle to the horizontal, therefore, VB in vector form will be this. So with that, we can now go and use the vectors we have got. So we know this formula, VC minus VB. So substitute for VC, substitute for VB to come up with this. But remember, the question wants magnitude and direction. So magnitude will be this squared plus this squared, everything under root to give you this. So here, to get the direction, we have positive horizontal and negative vertical. Therefore tan theta will be equal to this, therefore theta is 83.41, and the direction will be south 83.41 degrees east as before. So any of the two methods is okay. That was relative velocity. Now we shall go to the next part, which is true velocity. Now suppose that the true velocity VB of body B is known, and that the relative velocity of A relative to B of a body A relative to body B is also known. So if this is known and this is known, it implies that the true velocity VA of body A can also be got geometrically with the help of the formula that we already know, that when I expand this it will be VA minus VB. So when I want to make VA the subject, I'll take this on this side to come up with VA equal to relative velocity plus true velocity of B. Now remember, this is vectorially. That means that geometrically you are going to first draw this, and where it stops you add on this velocity. That's what geometrical means. And this VA will now be called the true velocity of A. So with that, we shall go through these questions. Question 1. To a girl running at 6 meters per second on a bearing of 155 degrees, a low flying bird appears. When you see this word appears, it implies that what they are going to give you is a relative velocity. So appears to be moving at 7 meters per second on a bearing of 250 degrees. Find the true velocity of the bird. So method 1, we shall start with the girl. Bearing is 155, so that means that from here up to here is 155. Now 155 minus 90 gives you 65, which is here. Then now for the relative velocity, this is the relative velocity of the bird relative to the girl, because now in this case it is the girl who is observing. So velocity of the bird relative to the girl is this, 7 meters per second, and the direction was bearing of 250, meaning that from here up to here was 250. Therefore, to get this remaining part, it will be 270 minus 250, which is 20. So now next is to add the two to come up with one complete velocity diagram. So it is up to you to choose. You can either start with this or start with this. Any of the two is okay. So in this case, to make it to be a little different, let me start with this velocity of the girl, and then where he stops, I'll add on this velocity, relative velocity. Then from there, I'll join from start to end to get my true velocity. Now the diagram is the same if you start with this. For example, if I'm going to start with this, it will be in this form first of all, and where this one stops, I'll add on the velocity of the girl, and where you stop, I'll join from here to here to get this resultant true velocity, which is the same as this. So any of the two diagrams is okay. Now I've managed to get an angle inside the triangle, meaning I can proceed. Therefore, by cosine rule, I can get the velocity of B, which will be 8.814. Then by sine rule, I can get theta, which is 52.29. That means that the bearing will be 90 plus 65 plus 52.29. From here up to here, there is this 90, there is this 65, and there is this theta. So when they ask for velocity, they want magnitude and direction. So you have got the true velocity of the bird and the direction. Now we shall go to vector approach. So vector approach, still I have to first make the simple sketches to help me get the vector form. So that is for the girl. Then for the relative velocity, it will be that, and vector form, it will be that. Therefore, I'll come and say that from this, the true velocity VB is equal to this plus that. So I'll come and add the two and come up with this as the velocity in vector form. Then I have to change it in terms of magnitude and direction. So magnitude is this as before. What about direction? So negative horizontal, negative vertical. Therefore, tan theta is this, implying that theta is that. But remember, they want direction, so bearing will be from here up to here, meaning that beta will be 270 minus theta, which is this. Therefore, the true velocity of the bird is that in the direction this. So that was question 1. Now we shall go to question 2. Question 2 says, to a person on a ship A moving due east at 15 kilometers per hour, ship B appears to be moving at 12 kilometers per hour in the direction north 30 degrees east. Find the true velocity of ship B. So still we shall go through the same procedure. Method 1, geometry, first draw simple sketches, then draw the one for the relative velocity. After that, you can join the two. So in question 1, we began with the true velocity followed by the relative velocity. Now here we're going to start with the relative velocity followed by the true velocity. Any of the two is okay, the order does not matter. So this is the relative velocity, then followed by the true velocity, which is this. Then line from start to end will be your true velocity of B. Therefore, still by cosine rule, I can get the velocity of B, and by sine rule, I can get the value of theta. Then therefore the direction is north, this plus this, which is 30 plus theta, and that will be the direction they wanted. So we have got the velocity and we've got the direction. So let's also look at the second method, which is vector. So still we have to draw some simple sketches to help you get the vector form. That is VA, then the relative to be that. Therefore, come and code the formula, then make VB the subject, then substitute, and this will be the vector form of the true velocity of B. I have to get the magnitude, I also have to get the direction, so positive horizontal, positive vertical. Therefore, tan theta is equal to that, implying that theta is this. That means that the direction is that. And that's what they wanted. So now shall go to question 3, which came from UNEB 1994, paper 1, question 3, and says, to a motorist traveling due north at 40 kilometers per hour, the wind appears to come from the direction north 60 degrees east at 50 kilometers per hour. Find the true velocity of the wind. Then if the wind velocity remains constant, but the speed of the motorist is increasing. Find his speed when the wind appears to be blowing from the direction north 45 degrees east. So here there are also two methods, so let's begin with the geometrical method. You are going to first make simple sketches. Then you can make the main sketch. So like I told you, it's up to you to choose where to start from. Now here I've begun with the relative velocity. After that I'll follow it with the true velocity of the motorist, which is here. So this is the relative velocity followed by this, and the line journey from start to end is the true velocity of the wind. Now the good thing, I've managed to get an angle inside the triangle, so I can proceed cosine rule. I'll get VW as this. So that is the magnitude, but I also need the direction. Therefore by sine rule, theta will be this. So you come and say that the direction is north 70.89 degrees east. So that was Roman 1. Then Roman 2, if the wind velocity remains constant but the speed of the motorist is increasing, find his speed when the wind appears to be blowing from the direction north 45 degrees east. So still we shall first make independent sketches. So here we don't know the magnitude of this and also of this. So we shall come and draw a complete diagram. So this true velocity of the wind was got in Roman 1 and also the direction. Then from there we shall add on this reversed velocity of the motorist. And after that we shall join from here to here to get the relative velocity. Okay. So now that we have finished our triangle, we shall come here and use sine rule to get this reverse velocity. Now I'm putting there magnitude because, like I told you, the negative shows that you have reversed, but in the calculations you must use magnitudes. So this over sine this will be equal to this over sine this, to give you Vm as this. Therefore the speed of the motorist will be that. Now we shall go to the vector method. So vector method for Roman 1, so we shall draw independent sketches to help us get the vectors. So now that I have this and this, I'll come and code the formula, make VW the subject, substitute to come up with this velocity vector. But remember, I'm interested in magnitude and direction. Magnitude is that, then direction, I'll first draw a right angle triangle with negative horizontal, positive vertical, Then I can use tan theta, which gives me theta as this, and the direction is as before. So that was Roman 1. Then for Roman 2, if the wind velocity remains constant, but the speed of the motorist is increasing, find U speed when the wind appears to be blowing from the direction of this. So shall let the velocity of the motorist magnitude be the speed be that, and the speed of the relative velocity to be y. Therefore, from here we shall say that Vm in vector form is 0x because it is entirely vertical. Then relative velocity will be this. Then I'll quote the formula and then substitute. So when I equate the one up, the I components, I'll come up with this line. Therefore, y is that. What about when I equate the j components? I'll come up with this, substitute for y, and make x the subject. So I've got the speed of the motorist, which is x, and that's what they wanted. So before we proceed, I would like to mention some of the books we have written. So if you're watching this video, then I strongly believe that even these books will be beneficial to you in both math and physics. So math, A-level math, there are 3 books. There's one for math paper 1, which is this, and also there is math paper 2, which is that, and there is a question bank, which is topical, having years from 2020 up to 1988. That is principal math. Then for subsidiary math, it is only one book called subsidiary math. Is only one paper. Then for A-level physics, we have physics paper 1, we have physics paper 2, and we also have the topical question bank. Then for O-level physics and math, there is physics volume 1 of 2, which has topics for senior 1 and senior 2. Then we have physics volume 2 of 2, which has topics of senior 3 and senior 4. And we also have the math topical question bank. So in case of any of these copies, you can contact the author on these numbers. The first one is also on WhatsApp, but the second one is only calls or texts. What you should know is that I'll be very glad if you call to order for copies. So now shall go to question 4, which came from UNEB 1988, paper 2, question 5b, and says, to a cyclist, note this word to, a cyclist riding due south at 20 kilometers per hour, a steady speed appears to be blowing in the direction to 40 degrees. When he reduces his speed to 15 kilometers per hour, the wind appears to blow in the direction 210 degrees. Find the true velocity of the wind. So this word appears means it is a relative velocity. This one is not the true velocity of the wind, it is just the relative velocity of the wind to this cyclist. So here we shall also use both methods. Let's start with the geometrical method. So for the first motion, that is from here up to here. So like I told you, it is up to you to choose what to start with. You can either start with the relative velocity, or the velocity of the cyclist. You can either start with this or this relative velocity. So in this case, I was chosen to start with the relative velocity, and they've told us that the relative velocity is in the direction of the bearing of 240 degrees. So you come here, draw your compass, and measure off 240 degrees, and that will be the relative velocity. We don't know its magnitude, that's why we are just putting there v velocity of w relative to cyclist. Now there is this C1. Why? It is because there are two motions. The first motion is this, then the second motion is when he reduces the speed. So one will be C1, another one will be C2. Then where this one stops, we shall add on now the velocity of the cyclist. They said he's moving due south at 20 kilometers per hour. So we shall come and add on the south of 20 kilometers per hour. Then from there we are going to join from starting point to the end point, and that will be the true velocity. Okay, now the good thing, we have managed to get an angle inside the closed triangle. That is for the first motion. What about for the second motion? For the second motion, the speed of the cycle is reduced to 15 kilometers per hour, and the wind appears to blow in the direction of 210 degrees. So still it is up to you. You can either choose to start with the velocity of the cyclist or the relative velocity. So in this case, I've chosen to start with the relative velocity still, and the bearing was 210, which is this. I think realize now why we are putting here C1 to distinguish it from this relative velocity, because when the speed reduces, the relative velocity will also reduce. Then where this one stops, we shall add on the velocity of the cyclist. They said it just reduced the speed, but the direction remained the same. So we shall come and put here our 15. Then we shall join from starting point to the end point, and that will be your true velocity, which is this. Now here, true velocity of the wind is constant. That is why you are seeing this angle is alpha, and this angle is also alpha. The direction is the same, and the magnitude is also the same. Then from there, we know that angles of a triangle add up to 180. So this plus what is here must add up to 180. So if here there is something like beta, you will say that beta is equal to 180 minus 150 minus alpha, which gives you 30 minus alpha. So those are the two sketches. Now that we have finished to get an angle inside the triangle, we can proceed. Like I told you before, if you can't get an angle inside the triangle, then there is no way you can proceed. So now we can proceed by using sine rule or cosine rule. So for the first motion, we shall use sine rule and say that VW over sine 120 is equal to 20 over sine 60 minus alpha. Let's see where it's coming from. So VW corresponds to 120, and this 20 corresponds to 60 minus alpha. So when I make VW the subject, I'll come up with this, and I'll call it equation 1. Then I'll also go to the second motion. For the second motion, if we come here, for the second motion, we have VW corresponds to 150 degrees and 15 corresponds to 30 minus alpha. So we shall come here and use the sine rule still. So we shall come and say that VW over sine 120, over sine 150 is equal to 15 over sine 30 minus alpha. Therefore, when I make VW the subject, I'll come up with equation 2. Now we have two equations and two unknowns, meaning we can solve them simultaneously. So the easiest method to use will be substitution, because here I have VW, and also here I have VW. Therefore, I'm going to equate both equations in order to eliminate the VW. Now I have only one unknown, which is alpha. Therefore, I have to look for a way of making alpha the subject. So when I cross multiply, I'll come up with this line. The next is to expand. Remember, this is now compound angle formula. So when I expand, sine 30 minus alpha gives you this. And when I expand this, I'll come up with this. So compound angle formula was covered in trigonometry of math paper 1. So from this step to this step, what I've done, I've divided throughout by cos alpha. So when I divide throughout by cos alpha, this one cancels, remain with sine theta alone. Here sine alpha over cos alpha gives you tan alpha. Here cos cancels, remain with sine 60 alone. Here sine alpha over cos alpha gives you tan alpha. Then from this step to this step, what I've done, I have opened brackets, this bracket and also this bracket. Then from this step to this step, what I've done, I've collected like terms. Remember, this term has tan alpha and also this term has tan alpha. So I'll put it on one side. That's why you see it here. Then this one does not have tan alpha, so I'll take it this side. That's why you see it here. Now next is to factorize out tan alpha. So tan alpha is here. That means that I'll remain with this minus this, which is the denominator. And for the numerator, I'll have what is on this side, which is here. Now when I use a calculator, the whole of this gives you 0.1925. Then arctan alpha, I'll come up with 10.89 degrees. Now here we have used 4 decimal places, and here we have used 2 because an angle, for an angle, the highest degree of accuracy is 2 decimal places. But elsewhere it should be 4 decimal places in math paper 2. Now from equation 1, now that we have got alpha, I can either use equation 1 or equation 2 to get the value of VW. So if I choose equation 1, I will come and substitute for alpha. And be able to get the value of VW as 22.9117 kilometers per hour. And that will be the true velocity. Remember, velocity is the vector quantity. That is why you have to get magnitude and direction. Now that was the method of geometry. What about the method of vectors? Now for the method of vectors, for the first motion, if you have still draw simple sketches, independent sketches. For the cyclist, he was due south, and the vector will be 0, negative 20, negative because it's moving downwards. What about for the relative velocity? Relative velocity, it was in that bearing. But for vectors, we have to get an angle to the horizontal. That is why we have to get this remaining angle. So it will be 270 minus 240, which is 30. When I do that, it means I can write it in vector form. Because I don't know the magnitude, I will first let the magnitude of the relative velocity to be x. Then I can come and get the relative velocity in vector form. Negative because from here I'll move to the left horizontal, which is negative, and also move downwards vertically, which is also negative. Then I'm going to quote the formula that true velocity is equal to relative velocity plus the velocity of the cyclist or the observer. Relative velocity come and substitute, and also substitute the velocity of the cyclist. And that will be equation 1. That is for the first motion. What about for the second motion? For the second motion, it is only the velocity which reduced to 15 kilometers per hour. Then for the relative velocity, therefore this one, the vector is now 0, negative 15. Then for the relative velocity, the bearing changed to 210. Therefore, that means that here we shall have 60. And in vector form, we don't know the magnitude, so we shall first let it to be y. That means that the relative velocity will now be this. Then I'll quote the formula for true velocity is equal to relative velocity plus velocity of the observer. Relative velocity is this, observer is this. So now we have two equations and two unknowns. We have this unknown, this unknown. Therefore, what we shall do, we shall solve them simultaneously. So when I equate the two, I'm going to come up with this. Therefore, what I'm going to do, equality of vectors. For the I components, they can be equated alone, and also the J components can be equated alone. That is if you want, or you can just rearrange. So what I've done, I've taken this one this side and this one this side. Then when I simplify, I'll come up with that. Then equality of vectors, this will be equated to 0 and this will be equated to 5. So equating the horizontal components, I'll come up with that. Take this one this side to come up with this as equation 3. What about when I equate the vertical components? It will become this equal to 5. Then take this one this side to come up with this. So my aim now is to solve these two equations simultaneously to get the values of x and y. So when I say equation 4 divided by equation 3, it means that I'm going to get this divided by this on the left hand side, and also this divided by this on the right hand side. Now sine over cos gives you tan, and this one cancels, so I'll remain with tan 60 here, and yet nothing changes. Now we realize that I have only one unknown, which is x, so my aim is to look for a way of making it the subject. So I'm going to first cross multiply to come up with this, then collect like terms, bring this one this side to come up with this, then make x the subject, and that gives you the value of x as 5 kilometers per hour. So now that I have the value of x, it means that the VW can be got from this equation by substituting for x. Then I'll come up with that as the velocity vector. But remember, they want magnitude and direction. Therefore, magnitude of this velocity vector is this, which was similar to the one before. Then what about the direction? Direction, we shall have to draw negative horizontal and negative vertical. Then we join from start to end to get the true velocity here. Then from there it's a right angle triangle, so I can use tan theta to get the value of theta as 10.89, which is similar to the one before. That means that any of the two methods is okay. You can either choose to use geometrical approach or vector approach. Now we shall go to what we call relative path. So consider two vessels A and B which are in motion, each moving along a specified path. The relative path of A to B is the path which appears to be taken by vessel A as viewed by the observer in vessel B. So it should be noted that this will not be the actual path taken by vessel A. It is just a relative path. So here, vectorially, we shall use R to denote the relative displacement. So RA, vector of RAT and vector of RBT are the paths taken by the vessels A and B at any time t, expressed in vector form. So note that they should be in vector form. That is why there is a tilde here and a tilde there. So now that we know this, we shall come and say that the relative path of A to B is denoted by RABT, and it's expanded in a similar way we did for relative velocity. So we start with what is here followed by what is here. So this t means that at any time t. That means that when you substitute t, you can get at that time, the relative path at that time. So now we shall go to the equation of the path. Suppose a particle A starts from point X with position vector RA tilde and moves at a constant speed of VA tilde to point Y in time t as shown below. So this is the illustration they are saying. The initial position vector OX of the particle is denoted as RA tilde, which is here, because the particle is at this point. Then the displacement vector XY of the particle after a time t is given by, remember, distance is equal to speed times time, so it will be time taken times the speed or the velocity to give you t VA tilde. Now what you should note is that time is not a vector. Time is a scalar, that's why there is no tilde. The tilde is only on the velocity. Then the final position OY of the particle is noted by RAT tilde, which is this, and can thus be got as follows. We shall say that to move from O to Y, I think remember that O level vectors, to move from O to Y, it will be this equal to from O to X plus from X to Y, which is this. And the good thing, I already know OX is RA, and I already know that XY is T times VA. Therefore, OY, which is RAT, will be equal to RA plus T times VA. So this formula is also familiar because we covered it under motion in a Cartesian plane, but this time we shall be using it for relative displacements. So this will be the equation of the path taken by particle A. Therefore, when I substitute the value of t here, I'll be able to get the position vector of that particle, of particle A at that time. Now we shall go to what we call relative displacement. So suppose two particles A and B start simultaneously from points with position vectors RA tilde and RB tilde, with moving with constant velocities VA tilde and VB tilde respectively. It implies that the equation of the path taken by particle A is given by this. We have already seen that in the previous slide, and that taken by particle B will be this. Therefore, the relative displacement of A to B will be denoted by this. So this is the relative displacement of A to B at any time t. When there is this t, it means at any time t. When there is no t, it means it's the initial relative displacement. Now we already know that this one can be expanded to give you RAT minus RBT. And I already know RAT is this and RBT is this. So what I'm going to do, I'm going to substitute for RAT and for RBT. Then from there, I will try to open brackets to come up with this. Remember, this and this gives you a negative. Then after that, I'm going to try to rearrange, put t's alone and without t's alone. So this and this, pair it to give you this. Then this and this, pair it to give you this. Then from there, I'll remember that RA tilde minus RB tilde is the same as RAB, and also VA tilde minus VB tilde is the same as VAB. I think you remember that. Therefore, in general, RABT is equal to RAB plus times VAB. So RAB is now the initial relative displacement of particle A to B, and RABT is the relative displacement of particle A to B at any time t. So now we shall go through these questions. Question 1 says, an object P passes through a point whose position vector is 3i negative 2j with constant velocity I tilde plus j tilde. At the same instant, an object Q moving with constant velocity 4i minus 2j passes through the point with position vector I plus 4j. Find Roman 1 the displacement of P relative to Q in time in t seconds, and Roman 2 the distance between P and Q after 5 seconds. So P relative to Q, they want RP Q T. So shall come and say that RPQ this is the initial relative displacement will be equal to RP minus RQ. So we are given this and we're also given this, so we subtract to get the initial relative displacement. What about the relative velocity? Relative velocity is still this minus this gives you the relative velocity. That relative velocity is constant. Therefore, at any time t, RP T will be equal to initial relative position displacement plus the time times relative velocity. So you already got the initial relative displacement and also relative velocity. Substitute and be able to come up with the relative displacement at any time t. Now that was Roman 1. What about Roman 2? For Roman 2, they want the distance between P and Q after 5 seconds. That means that we shall come and where there is t, we shall substitute 5 to come up with this. Now this one is the relative displacement after 5 seconds, but they want the distance between the two. So distance is a magnitude, therefore you have to get this magnitude, which will be now the distance. Now you must be keen to realize that we are not adding the unit on distance or displacement. Why? It is because in the question they didn't give units. So in vectors, when they don't give units, you should also not give units. That was question 1. Now question 2 says a particle P starts from a point with position vector 2j plus 2k with a velocity j plus k. A second particle Q starts at the same time from the point whose position vector is negative 11i minus 2j minus 7k with a velocity 2i plus j plus 2k. Find Roman 1 the displacement of Q relative to P in time t. Then Roman 2 the distance between P and Q after 6 seconds. So we shall first get the initial relative position, subtract the 2 to come up with this. Then also get the relative velocity, this minus this to give you this. Therefore now I can come and substitute r2pt is equal to r2p plus t times v2p. So substitute this and also this, and that will be the answer they wanted. Then for Roman 2, when it comes for Roman 2, they wanted the distance between P and Q after 6 seconds. So we shall come here and substitute where there is T, we shall put there 6. And shall come up with this. So this is the displacement, but they want distance, so we have to get the magnitude. So the magnitude will be equal to this. So note that we are also not putting units because in the question there were no units. So now we shall go to collision of particles. Now suppose two particles A and B start simultaneously from points with position vectors RA and RB. So by now I believe you know what these ones mean. And move with constant velocities VA tilde and VB tilde respectively. If these particles collide after a time t, it implies that the relative displacement of A to B at that time is equal to 0, meaning that there is no distance between them. Remember, this relative displacement means the distance between the two particles, but when they collide there will be no distance between the two, so that means that it will be equal to 0. So that's what they mean by relative displacement at any time t being equal to 0. And we already know that this one can be expanded to be equal to this. What does that mean? It means that for collision the whole of this will be equal to 0. So this is the formula which we shall use in this part of collision of particles. But what you should note is that this formula, these are vectors. These are vectors. So RAB is equal to the initial displacement vector of A to B, T is the time taken for collision to occur, and VAB is the relative velocity of A to B. So that we shall go through these questions. Question 1 says, at noon, the position vectors R tilde and velocity vectors V tilde of two ships A and B are as follows. So these are the position vectors and velocity vectors. Show that if the two ships do not alter their velocities, that means that the velocities remain constant, a collision will occur, and find the time at which it occurs and the position vector of its location. So first of all, we shall first get the initial relative displacement. We know RA, we know RB, subtract the two to come up with this. So in the question, they did not specify whether to use RA to B or RB to A. So how do you know that I should use the relative velocity of A to B? Now for you to know, you look at the velocities. The one with the highest speed is the one which is relative to the other. So for example, if I get the magnitude of this, it will be greater than the magnitude of this. Therefore, I should say relative velocity of A to B. So the one with the highest velocity is the one which is relative to the other. That works only if they don't specify which relative velocity to use or relative position to use. Then for relative velocity of A to B will be this minus this to give you this. Now here we are adding units because in the question the units were there. So we shall come here and say that for collision to occur, we shall remember that this will be equal to 0. Therefore, I'll come and substitute for the initial relative position and the relative velocity. Then, using the I components, I'll come up with this, and I'll get t as 1/3. Then when I use the j components, I'll come up with this and get t as 1/3. Now here, you realize that the value of t is the same for all components. Therefore, we shall come and conclude that since t is a scalar and this plus this is equal to 0, then collision will occur. And the time taken for collision to occur will be 1/3 hours. So I can change to minutes, which is 20 minutes. They told us that it started at noon, therefore add on 20 minutes to come up with a time which is, now this time is in 24-hour clock, therefore you'll come here and say that collision will occur at 12:20 p.m. They also wanted to know the location, so I can either use RAT or RBT, any of the two is okay. So if I use RAT, I'll come and substitute for RA and T and also for VA to come up with this as the position vector. Then I'll conclude that the position vector of its location, of the location of collision, will be this. So if I use B, I'll still get the same answer. So any of the two is okay. Then question 2 says, a ship is sailing due north at a constant speed of 12 kilometers per hour. The destroyer sailing at 36 kilometers per hour is 30 kilometers due east of the ship. At this moment, the destroyer is ordered to intercept the ship. Find part A, the course which the destroyer should take. Part B, the velocity of the destroyer relative to the ship. And part C, the time taken for the destroyer to reach the ship. The assumption is that both ship and destroyer do not change their velocities. So now here we shall use two methods. Now in question 1, we used only vector method. Why? Because the question was given in vector form. If the question is given in vector form, then you should only use vector approach. But if the question is given in magnitude and direction form, then you can choose. It is you to choose whether to use geometrical approach or vector approach. The examiner cannot specify that you use this method. It is you to choose which method is easier for you. So first we shall start by making sketches. This will be the velocity of the ship. Now we are reversing it because the question said the velocity of the destroyer relative to the ship. So relative to this. So it is this one we have to reverse. Therefore, I draw the velocity of the ship and reverse it. Then from there, I will locate the initial positions of both the destroyer and the ship. Now, if you look at this, the initial position, they said a ship is sailing due north, okay? The destroyer is sailing this, okay? Then at this moment, the destroyer is ordered to intercept. So it is 30 kilometers due east of the ship. So destroyer is 30 kilometers due east of the ship. Therefore, it means that we shall stand at the ship at the position of the ship and locate eastwards. So east is this side, and this distance will be 30 kilometers. Now we are not putting the 30 kilometers because what we are drawing is a velocity diagram. So along this line, joining the two positions is where the relative velocity must be. Because it is d relative to ship, it means it starts from d and goes to the ship. So the order matters. If this was ship relative to d, it means that it would have started from this going towards d. So the order matters and the direction of the relative velocity matters. It depends on what is here. So that is the initial position. Then from here, where this ship is, we shall locate this negative or the reversed velocity at the ship. Like I told you, this negative means I'm reversing the velocity, but in the calculations we use magnitude. And that explains why here I'm not putting negative 12, I'm just putting 12 because I'm interested in the magnitude. Now from this point up to this point, that will be the velocity of the destroyer. So we are doing that because in the question they did not specify the velocity of the destroyer, so they don't specify the direction of the destroyer, rather they wanted it. If you look at Roman 1, here they said find the course which the destroyer should take. So you don't know the direction of the destroyer. That is why we first put this reversed velocity. After that we can locate the velocity of the destroyer. Now the good thing, this is a right angled triangle, and therefore I can use, when I use this angle, this will be opposite, this will be adjacent, therefore I'll use sine theta equal to 12 over 36, and therefore theta will be 19.47 degrees to 2 decimal places. Angles, the highest accuracy is 2 decimal places. Therefore the bearing will be from here up to here. Now from here up to here is 270 plus theta, which gives you the actual bearing they want, which is 289.47 degrees. So that was part A. Now we shall go to part B. So part B said find the velocity of the destroyer relative to the ship. So they want this relative velocity of the destroyer to the ship. So, and the good thing, this is the right angle triangle, so you can use Pythagoras theory. So this 36 is the hypotenuse, therefore we shall put a minus. That is why we are putting a minus here. So this will be equal to the square root of 36 squared minus 12 squared. When you use a calculator, it gives you 33.9411 kilometers per hour due west. Remember, it is moving due west. So velocity means you have to get magnitude and direction. That was part B. Now we shall go to part C. Part C, they want the time taken for the destroyer to reach the ship. So time taken is equal to distance ds divided by speed along ds. Remember, we said the speed we use is the relative velocity, and the distance is the distance along the relative velocity. For example, if you look at this, the distance along the relative velocity is ds. That's why you're using distance ds. Though I told in the question that it's 30 kilometers. So we shall come and substitute for distance and also for relative velocity to give you 0.8839 hours. Now that was geometrical approach, but you can also answer this question using vector approach. So for vector approach still, we have to first make some simple sketches. One for the velocity of the ship, and also, so here we do not need to reverse. Reversing is done when you are using geometrical approach. So just write the velocity as it is, and in vector form it will be 0.12 kilometers per hour. The magnitude of the velocity of the destroyer was given as 36. They didn't give the direction, that's why we can't draw its sketch. But the relative position of D and S, so the position of D and S were given, so we shall get its sketch. Now here we shall put kilometers here. Now this one, it is RDS, means that you stand at S and you locate where D is. So when I stand at S, D will be 30 kilometers east. That is why there is 30, 0 in vector form. Then we shall come and recall the condition for collision or interception. So interception, collision, they mean the same. So the condition is that this plus this is equal to 0. Therefore, I will come and substitute. My RDS is here, and VDS is VD minus VS. VD is not known, but VS is known, so I can substitute for VS. Then when I open brackets, I'll come up with this. When I make this the subject, I'll come up with this. And when I add this to this, I'll come up with this, because this is 30 plus 0, which is this, and 0 plus 12t, which is this. Then when I make VD the subject, I'll come up with this. Then from there, I'll remember that the magnitude of VD is 36. Therefore, I'll come and get the magnitude of this vector. This is a scalar, it can remain outside. Then this one will be 30 squared plus 12t squared, everything under square root, is equal to 36. Then when I bring this one this side, I'll come up with 36t. Then square both sides to come up with the whole of that line. So now the good thing, I have only one unknown, which is t. So I have to simplify and look for a way of getting t. So from here to t, I've expanded this is this, and this is this. Then collect like terms, and for that you look for making t the subject. I'll come up with this as the time taken. And remember, it was the same as we got under geometrical approach. Then from there, I'll come and substitute my t here to get the velocity vector of D. And the vector will be this. Now I also I have to get direction and magnitude. So the direction is got by drawing this right angle triangle, negative horizontal, positive vertical. So tan theta will be this, therefore theta is this. Therefore, in terms of bearing, it will be from here to here, it will be 360 minus theta, which is this as the one before. So that is what they wanted in Roman 1. If you look at this. Then Roman 2, they wanted the velocity of the destroyer relative to the ship. So this will be equal to VD minus VS. We are doing this because these are vectors. So substitute for VD, substitute for VS, subtract to come up with this. So the velocity of the destroyer of the ship is this. So the magnitude is this because it is entirely horizontal, due west. West, because of this negative horizontal. Negative horizontal means this, to the left. That was part B. What about part C? So part C, they want the time taken for the destroyer to reach the ship. So time taken, remember we already got it in Roman 1, so that is what we shall just put, and here we just state. So that was question 2. Now we shall go to question 3. Question 3 says a helicopter is flying on a course of 060 degrees with a speed of 100 kilometers per hour. An aeroplane which is 50 kilometers due east of the helicopter can fly at 200 kilometers per hour. What course should the aeroplane take to intercept the helicopter? After how long will they intercept? So here, because the question is given in terms of magnitude and direction, we can choose to use either geometrical approach or vector approach. So we shall look at both of them. Let's start with geometrical approach. Now for geometrical approach, we shall get the known velocity whose direction is known. So it is the helicopter whose direction of the velocity is known. Therefore we shall get it, put it here, and reverse it. Then after that we shall locate the initial positions of the helicopter and the aeroplane. So they told us that the aeroplane is 50 kilometers due east. It means that when I stand at the helicopter, the aeroplane will be due east. Now we are not putting these kilometers because what we are drawing is a velocity diagram. What we do, along that very line, joining the initial positions, we shall put the relative velocity. And the direction matters because here it is A to H, meaning the arrow must point from A going to H. Then next we shall come and put this reverse velocity at point H. We are interested in the magnitude, so this is that. Then from there we are going to join from here up to here, and that will be the velocity of the aeroplane. Okay, now we have finished our triangle, and the good thing, we have already got an angle inside the triangle. Therefore we can proceed. So if you don't get any angle, there is no way you can proceed. So they want the cos. Cos means that we have to first get this value of alpha. Then after how long, that is time, meaning we have to first get this relative velocity. So let's do that in the next slide. So from here you realize that here I can use sine rule. There is this and there is also this. So by sine rule, I'll come up with alpha as 14.48 degrees. So that means that the bearing will be 270 plus alpha, which is 284.48. So that will be the course set by the aeroplane. So here they also wanted the course set by the aeroplane. That was the first question. Then after that they also wanted the time taken, meaning you have to get this relative velocity, but there's no way you can get that relative velocity when this angle is not known. Therefore I'll come and remember that angles of a triangle add up to 180 degrees, and when I remember that, I'll come and get the value of theta as 135.52. Then from there I'll use sine rule. Sine rule will be v relative velocity over sine 135.52 is equal to 200 over sine 30, and with that I'll be able to get the relative velocity. Now the time taken will be the distance AH over speed along AH, which gives you 0.1784 hours. So that was geometrical approach. Now shall go to vector approach. So vector approach, still you have to make the sketches. One for the helicopter, which is this. Another one for the initial positions. So magnitude of VA is known, but the direction is unknown. Then the relative position of A to H means that you stand at H and you locate where A is. So A is 50 kilometers east. That is why we have 50, 0. Then for collision to occur, this has to be equal to 0. Therefore, I'll come and substitute this and also this. Then open brackets, open the box bracket to come up with that. Then make this one the subject, take this one this side, and this side to come up with this. Then make VA the subject. After that, remember that the magnitude is equal to 200, therefore get the magnitude of this, which is this, equal to 200. Then take this one this side and square both sides to come up with this line. Then simplify, you come up with that. So what I've done, I've taken this side to come up with this, and this one has remained the same. When I open brackets, I'll come up with this. Simplify further, you come up with this. Now the good thing, I have only t as the only unknown. Therefore, I can easily get the value of t. So this is a quadratic. I can reduce it and then use bulldozer method to come up with t as this or t as this. Then from there, remember that t will not be negative. Therefore, t is equal to 0.1784, which is the same as before. So the aeroplane and the helicopter will intercept at 0.1784 hours. So when I substitute for t, I can be able to get the velocity of A. So this will be the velocity vector of A, but remember they want its direction. So negative horizontal, positive vertical. I'll come and draw the right angle for negative horizontal and positive vertical. So it's the negative horizontal, positive vertical, and this will be the velocity of A. That means that I have to get the value of theta. So value of theta, tan theta will be this, therefore theta will be 75.52. And in terms of bearing, it will be 360 minus theta, which is 284.48, and the same as before. So any of the two methods is okay. You can choose geometry or you choose vector. Now we shall go to question 4, which came from UNEB 1995, paper 2, question 3, and says, in the Gulf waters, a battleship streaming northwards is 16 kilometers per hour. Streaming northwards at 16 kilometers per hour is 5 kilometers southwest of the submarine. Find two possible courses which the submarine could take in order to intercept the battleship if its maximum speed is 12 kilometers per hour. So here there are two methods. You can either use geometry or vector. So let's start with geometry. For geometry, you shall get the velocity whose direction is known and reverse it. So this is 16, it is northwards, so we shall reverse it to be southwards. Then from there we shall locate the initial positions of the submarine and the battleship. Now they told us that battleship is southwest of submarine. So we shall stand at submarine and locate southwest in order to get the position of the ship. So 45, because southwest means 45 degrees. Then from there, I'll get this reverse velocity and place it at B. So let's do that. Okay, then next I'll join from here to here, and that will be the velocity of the submarine. Okay, the good thing, I've got an angle inside the triangle, meaning I can proceed. If you don't get any one angle inside the triangle, there is no way you can proceed. So the question wants the two possible courses which the submarine could take. Course of submarine meaning that we have to first get the value of alpha. So sine rule, this has this and this has that. So by sine rule, alpha will be, there are two angles, there is this and also this. I think remember how to get multiple angles in trigonometry, in the video for trigonometry. So sine will be positive in the first and second quadrant. So the first quadrant is this one, which is 70.53. Then the second quadrant, here there will be 70.53, meaning that from here to here it will be 180 minus 70.53. When you get a calculator and press that, you come up with 109.47. And those will be the two possible directions. But they want them in terms of bearing or compass direction. So for alpha equal to this, I'll come and first get the value of theta. Then also for alpha equal to this, I'll also come and get the value of theta. So there are two values of theta, implying that the two possible directions will be north 64.47 degrees west and north 25.53 degrees west. So that was geometrical approach. Now shall go to vector approach. So vector approach, still you need to make some sketches of the velocity whose direction is known, and also for the initial positions. So this vector form is that. Then you can come and get the position of S relative to B. So it means that you stand at B and locate S. That will be positive horizontal, positive vertical, which is that. Therefore, for interception to occur, this must be equal to 0. Therefore, I'll come and substitute for this and for that. Then open brackets, make this the subject. After that, you have to make Vs the subject. But I remember that magnitude is equal to 12. We are given the question. Therefore, I'll come here and get the magnitude equal to 12. Then take this to this side and square both sides, come up with this. Then expand to come up with that. Simplify to come up with a quadratic. Use bulldozer method to come up with the values of t. So there are two values of t. Therefore, remember that Vs is that. Therefore, when t is equal to this, I'll come up with this, which gives me this vector. Now for that vector, I will have to get its direction. Negative horizontal, positive vertical. So tan theta will be equal to this. So this was supposed to be theta 1 is equal to that. Therefore, theta is equal to this. So this is one of the directions. What about when t is equal to 0.3265? When t is equal to this, I'll come and also get the corresponding value of Vs in vector form. Then I will also locate negative horizontal and positive vertical. Then this is supposed to be tan theta 2, so tan theta 2 we have 64.47. So those will be the two possible directions. You can either use geometry or vector. So now we shall go to question 5, which came from UNEB 2010 paper 2 question 15, and says two aircrafts P and Q are flying at the same height. P is flying due north at 500 kilometers per hour, while Q is flying due west at 600 kilometers per hour. When the aircrafts are 100 kilometers apart, the pilots realize that they are about to collide. The pilot of P then changes course to 365 degrees and maintains the speed of 500 kilometers per hour. The pilot of Q maintains his course but increases the speed. So the direction increases, the direction changes, speed magnitude remains the same. Determine part A, the distance each aircraft would have traveled if the pilots had not realized that they were about to collide. Then part B, the new speed beyond which the aircraft Q must fly in order to avoid collision. So now here they have not specified that the velocity of this relative to this. So what we are going to do, we shall compare the magnitude of the speeds or the velocity. This one is bigger than this, meaning that it will be the velocity of Q relative to P. So that means that it is the velocity of P which we are going to reverse. So I'll come here and make a sketch of the velocity of P and reverse it. Then also sketch the velocity of Q. Okay, therefore the relative velocity will be got by first drawing the velocity of Q followed by the reversed velocity of P. So the velocity of Q is this. Then where it stops, I'll put there the reverse velocity of P, which is that. Then from here to here, it gives you the relative velocity of P to Q. Now we are putting these positions because the relative position, the relative velocity is along the line joining the initial positions. So we think this is the right angle triangle. Therefore, we shall come and say that for the distance each aircraft would have traveled if the pilots had not realized that they were about to collide. So I'll come and first get the relative velocity by Pythagoras theory, which is this. Then tan theta is equal to 600 over 500, which gives you theta as 50.19. The time taken will be distance to P over the relative velocity, which gives you this. So this will be the time taken. But the distance traveled by each, so distance traveled by P is equal to time times velocity of P, which gives you 64 kilometers. That of Q is time times velocity of Q, which gives you 76.8 kilometers. So for part B, they want the new speed beyond which aircraft Q must fly in order to avoid collision. Now remember, pilot P changed the course to this and maintained the speed of this, but pilot Q maintained the course of this due west but increased the speed. So you'll come and try to make the sketch. So let v be the critical speed, or the speed beyond which CHU must exceed. So P is this. They told you that the new direction is bearing of 345 and the angle to the horizontal is 75. So I have to reverse it still, so I have to get this. Then for CHU, I know the direction but I don't know the magnitude, so V CHU will be equal to V. So I'll come here and draw a complete velocity diagram. So first of all, we are given the position vectors. We are given the initial positions. Previously we saw them that P and CHU, P is here and CHU is here initially, and this theta was 50.19. So that is why we are putting them there. The next is to locate this V CHU, which is this. So this is 90, meaning that this remaining angle will be 39.81. Then from there, I will add on the reversed velocity to complete my triangle. So by sine rule, V over this is equal to 500 over this. Therefore, V is 708.8739. So the new speed beyond must be beyond this for collision not to occur. Now that was geometry method. Now shall go to vector method. So still we have to make the independent sketches. For VP, we also have to make the one for V CHU. And its velocity vector will be this. The magnitude of the relative position is known as 100, the distance apart. Therefore, relative velocity will be V CHU minus VP. Substitute for V CHU and also for VP to come up with this. Then for collision to occur, this must be equal to 0. Therefore, I come and substitute this one. I don't know it, but this one I know it. Then make this one the subject. I'll come up with this. But I remember that the magnitude is 100. Therefore, come and get the magnitude of this equal to 100. Square both sides and make T the subject. So if I make T the subject, I'll come up with T being equal to this. Therefore, the distance traveled by P is equal to time times the velocity of P. You have got time and you know the velocity of P. So now here we have to get magnitude. So magnitude of this velocity will be this, which gives you this as the distance traveled. Then the distance traveled by CHU is times the magnitude of V CHU. So magnitude of this is this, therefore you come up with this as the answer, which were similar to the ones as before. Then for part B, remember that P changed the course to this and maintained the speed, while CHU changed course and maintained speed. So you come and say that at the point when CHU changes speed, T is that. Therefore, the relative position will be this. Substitute for T to get the now. We are doing this to get the new initial positions at the point when the speed changes, which is this. Now let v be the critical speed of q. So first of all, v2 will now be this. Therefore v2 in vector form, it will be that. For vp it will be this. Therefore in vector form it will be that. Then the relative velocity of q to p is given by this. Simplify to come up with that. So at the point of collision, this will be equal to 0. So I'll come and substitute initial relative position when they change speed, relative velocity, and time there. So when I rearrange it, I'll come up with this, because I've taken this one this side. Now we have two unknowns. We have v and t. Therefore what I'm going to do, I'll first equate the vertical components to get the value of t. After that, I'll equate the horizontal components and get the value of v. So simplify and make v the subject. So v will be this, which is similar to the one before. Therefore the new speed must be beyond this. So before we proceed, I would like to mention some of the books we have written. So if you're watching this video, then I strongly believe that even these books will be beneficial to you in both math and physics. So math, A-level math, there are 3 books. There's one for math paper 1, which is this, and also there is math paper 2, which is that, and there is a question bank, which is topical, having years from 2020 up to 1988. That is principal math. Then for subsidiary math, it is only one book called subsidiary math. There is only one paper. Then for A-level physics, we have physics paper 1, we have physics paper 2, and we also have the topical question bank. Then for O-level physics and math, there is physics volume 1 of 2, which has topics for senior 1 and senior 2. Then we have physics volume 2 of 2, which has topics of senior 3 and senior 4. And we also have the math topical question bank. So in case of any of these copies, you can contact the author on these numbers. The first one is also on WhatsApp, but the second one is on the calls or text. What you should know is that I'll be very glad if you call to order for copies. Now we shall go to what we call closest approach. So if two bodies do not collide, there will be an instant at which they are closer to each other than they are at any other instant. And that is what we call closest approach. So closest approach is divided into 4 parts. One is time for closest approach, distance of closest approach, time and distance, and also cost. So these are the various questions which they can ask. They can ask you to get the time for closest approach, or they can ask for distance for closest approach, or they can ask for both, or they can ask for the cost. So all these ones will be seen also in this video. So let's start with time for closest approach. So the time for closest approach can be got using any of these 3 methods. So you can either get time for closest approach using this method, that initial relative position dot relative velocity over relative velocity squared. Note that they are magnitudes. So this dot has to be seen. I think you remember dot product and introduction to vectors. Or you can use this condition that the relative displacement at any time t and the relative velocity are perpendicular. So relative displacement is perpendicular to the relative velocity. That is why this dot this is equal to 0. Another method is the one for which you learned in your math, that maximum and minimum, the derivative must be equal to 0. So when I differentiate the relative displacement at any time t squared, it will be equal to 0. We put square so that we can eliminate the square roots, because differentiating square roots are not that easy. So these are the three methods which can be used. So any of the three, if you master any of the three, then you are good to go, because they will all give the same answer, as we shall see in the worked examples. Now these, I think, realize that these are, there is a tilde sign here, meaning that these should all be in vector form. Therefore, if a question is given in terms of magnitude and direction, you have to first convert it into vector, as we have been doing for collision. The geometrical approach for getting this time for closest approach is also there, but for this video we shall ignore it, so that, because we already have a number of methods to use, so we shall ignore the geometrical approach for time and distance. Geometrical approach will come in when we reach the part of cost for closest approach, because there, when it comes to cost for closest approach, it is the geometrical approach which is easier. For time and distance, it is the vector approach which is easier. So with those methods, let's go through these questions. So question 1 says, at 10 a.m. the position vector of ship P relative to ship Q at any time t hours is given by this. Part A, write down the velocity of P relative to Q. And part B, find the time at which the ships are closest together. So first of all, we shall get this which is given. This is I, this is J, and write it in column form. Then after that we shall split it, the one with t, without t alone, and the one with t alone. Now this one is similar to, this will be now the initial relative displacement of P to Q, and this will be the, this will be the initial relative position of P to Q, and this will be the relative velocity of P to Q. So in the question they asked you to write the relative velocity of P to Q, so we are going to write this. And that's what they wanted. So we are putting units because here there are units here and also here. So now we shall go to Roman 2, where they want you to find the time at which the ships are closest together. So we shall use all the three methods we have seen in the previous slide, and it's up to you to choose which method is easier for you. So method 1 is this one for dotting. So this dot this, you come and write it here, this dot must be seen over magnitude of relative velocity, so it will be this squared plus this squared. It would have been under square root, but remember there's a square here, so square root cancels with that square to remain with only this. Then you have to dot, so this times this gives you negative 42, this times this gives you negative 60 over 34. Now this negative this minus this, remember this magnitude sign means what is negative becomes positive. That is why this negative this minus this divided by this, it would have given you negative 3, but because there is a magnitude sign here, we shall ignore the negative. So they are given the starting time. So starting time was 10:30. We have to change it to 24-hour clock. Then plus these 3 hours to give you 13:30. So 13:30, when it comes to 12-hour clock, it is 1:30 p.m. That is method 1. Let's go to method 2. So method 2, we say that for closest approach, this dot this is equal to 0. Therefore, we shall come and substitute for this which was given and also this which was given. Now dotting the two, this dot has to be seen, so this times this gives you this, then this times this gives you this. Now here we have to look for making t the subject, and t will be equal to 3 hours, which is the same as this. So any of the methods is okay. What about method 3? So method 3 involves differentiating. So first of all, this squared is equal to this plus this squared plus that. There's no square root because of this square here. Then for closest approach, the derivative of this will be equal to 0. So I have to differentiate that. So when I differentiate, I will say bring down the power, reduce the power by 1 to get power 1, then multiply by the derivative of the inner bracket, which is negative 3. Then for this case, bring down the power, reduce the power by 1, then derivative of the inner bracket, which is negative 5. The next is to expand and simplify until you make t the subject. So t will be equal to 3 hours, which is the same as before. So any of the 3 methods is okay, because the question will not specify that you use this method or the other method. It is up to you to choose which one is easier for you. Now we shall go to question 2. Question 2 came from UNEB 2017, paper 2, question 16, and says, at noon, ship A is moving with constant velocity of 20.4 kilometers per hour in the direction north theta degrees east, where tan theta is equal to 1/5. That is ship A. Then a second ship B is 15 kilometers due north of A. Ship B is moving with a constant velocity of 5 kilometers per hour in the direction south alpha degrees west, where tan alpha is 3/4. If the shortest distance between the ships is 4.2 kilometers, find the time to the nearest minute when the distance between the ships is shortest. So first of all, we shall first get theta from here, arctan 1/5, which gives this. So the highest degree for angles is 2 decimal places. When it comes to alpha, tan alpha was this, therefore alpha will be arctan that. So next is make simple sketches. So for ship A, they said north theta degrees, so it is north 11.31 degrees east, and that is it. When we come to ship B, sorry, the positions, they told you that it is, let me see, 15 kilometers due north of ship A. So ship B, when I stand at A, I will locate north where ship B is. Then also ship B. So ship B, they said the direction is south alpha degrees west, which is south 36.87 degrees west. But for vectors, we are interested in the angles to the horizontal, so I have to get this angle and also this angle. Now with those sketches, I can now express them in vector form. So I'll come here and express VA in vector form and VB in vector form, after which I can be able to get my, so this is VA in vector form, this is VB in vector form, so I can get my VA relative to B, which is that. Then also relative position will be 0, -15, RA to B, because, for example, RAB means that you stand at B and you locate A. So when I stand at B, A will be downwards, that is why it is negative. So it is up to you to choose which method to use. So for me, I'll choose the first one, which I believe it is easier for me. So for it, if it's method 2 which is easier, you use it. If it's method 3, you also use it. So I'll come and substitute this and also this. Then in the denominator, I'll get the magnitude of this. Now when I dot, it means this times this will be 0, then this times this will be negative that. Then when I add these two, I'll come up with this. And when I use the calculator, remember this magnitude means what is negative becomes positive. So the whole of this divided by this gives you a positive time in hours. They say to the nearest minute, so to the nearest minute it will be a whole that is nearest whole number, which is 35 minutes. So when I add, remember the starting time was noon, which is 12. Now this is now 24-hour clock plus 35:00:35. It gives you 12:35. Therefore, in 12-hour clock, it will be 12:35 p.m. So that is how they get time for closest approach. Now we shall go to distance for closest approach. So the shortest distance or least distance for closest approach can be got using any of the three methods. So method 1 is by using this, which is initial relative displacement cross relative velocity over magnitude of relative velocity. So here note that this one does not mean multiplication. In vectors, we don't have a multiplication symbol. What we have, we call it crossing. So this is cross. So this cross this magnitude over relative velocity magnitude. So we already saw how to cross two vectors under motion in the Cartesian plane. So you can refer to it. The another method is by remembering that the distance for closest approach is minimum if this relative position or relative displacement between the two particles is minimum. So what you do, if you have already calculated the time, as we saw in the previous slide, because previously we have seen how to get time for closest approach. So if you get that time and substitute it into the relative displacement at any time t, its magnitude will be equal to the shortest distance of approach. That is method 2. Then method 3, you can choose to first get this magnitude, then you remember that this one is minimum at closest approach. We shall see how all these methods are used. So question 1 says, cars A and B are moving with respective velocities -2i plus 9j, I plus 8j meters per second. If the initial position of A relative to B is this, 12i minus 3j meters, find the shortest distance between A and B in the subsequent motion. So here we have the relative displacement as that. Then relative velocity will be, remember this is VA and this is VB. Therefore VAB will be equal to VA minus VB to give you -3.1. We are putting units because in the question they were units. Now method 1, we are going to look at all the three methods. So method 1 was for crossing. So what we are going to do, we are going to first cross. So this cross this, I'll come and substitute. Now how do we write? Remember, we have to write I. So this is I and this is J. So RAB was 12 -3, so we write it in this form. Then VAB was -3.1, so we write in that form. Some students confused and they write it in this form, which is not okay. So it's advisable you write horizontally, IJ. Then from there, to cross means it's like getting the determinant. So you say major diagonal product of major diagonal, which is this, minus product of the minor diagonal, which is 9. So 12 minus 9 gives you +3. Now that I've crossed, I can get my minimum distance. By quoting the formula, then substitute. So magnitude of this is 3. So this magnitude sign means that what is negative becomes positive. So this one was already positive, so it means that it remains positive. Then magnitude of the relative velocity is that. And when I use the calculator, the whole of this gives you this. That is method 1. What about method 2? So for method 2, still we quote the formula, then we substitute relative displacement, relative velocity over magnitude of velocity. So it is squared, that's why there is no square root here. So this times this gives you this, and this times this gives you this. Then this one simplified gives you 10. Now this magnitude means what is negative becomes positive. That is why you are seeing here positive 39. Divide by 10, you get 3.9 seconds. Now after getting time, then you can get your minimum distance. But before, you have to first get minimum displacement. So where there is t, you are going to put there the time, minimum time, which is 3.9, to come up with this as your displacement. But they want distance, so you have to get the magnitude, which will be this as before. Then method 3, we shall come and say that for closest approach, this is minimum. So what we are going to do, we are going to first get magnitude of this. So magnitude of this is this. Expand it, you come up with this. Then get a quadratic, then complete squares. Now to complete squares, I have to first make this coefficient positive 1 by factorizing out 10. So when I factorize out 10, I'll come up with this. Then from there, I will complete squares. This divided by 2 gives you 3.9, which is here. Then this one is here, then minus this square. So when I square this one, I'll come up with 15.21, which is there. So that is how they complete squares. We already covered completing squares under the topic of quadratics and polynomials, which is under algebra. So we can go there and review. So when I simplify, I'll come up with this, and there I'll say that this is minimum when this one is 0, because remember, as long as it has a square, it can never be negative, so the minimum will be 0. So when I equate it to 0, I'll get t as 3.9. Now that I've got t, I can come here and get my minimum displacement by substituting for t, and it will be this. Therefore the distance will be the magnitude, which will be equal to that. So all the three methods give the same answer. It is up to you to choose which one is easier for you. Then question 2 came from UNEB 2019 paper 2 question 9 and says car A is 80 meters northwest of point O. Car B is 50 meters north 30 degrees east of O. Car A is moving at 20 meters per second on a straight road towards O. Car B is also moving at 10 meters per second on another straight road towards O. Determine part A, the initial distance between the two cars. Part B, the velocity of A relative to B. And part C, the shortest distance between the two cars as they approach O. So the first thing to do is to make the simple sketches of the positions of O and A. So northwest means 45 degrees here. So this is now car A because it is moving from A towards O. What about car B? So we shall also make its sketch. So these sketches that enable us to transform the magnitude and direction into vector. So it's moving from B towards O and it's 10 meters per second. Therefore, relative position of A to B, first of all, we have to locate RA and RB. So RA will be, remember this is A, so it will be to move from here to move from A to O to A. It is horizontal, it is negative, vertical it is positive. That's why you see here negative 80, because they told us in the question they said 80 meters. That is why you see that 80. Then for B they told us 50. That is why you see this 50. So I'll come and say that this side is negative 80 cos 45, upwards it is positive 80 sin 45. Then for this one, this side is positive 50 cos 60, upwards it is positive 50 sin 60. When I subtract the two, I'll come up with RA relative to B, which is this in vector form. Then magnitude will be given by that. That is part A. So part A is asked for the initial distance between the two cars, which is the initial relative displacement. Then part B, they wanted the velocity of A relative to B. So they have to get this velocity in vector form, which is this, and this velocity in vector form, which is that. When I subtract the two, I'll come up with this. Then magnitude, remember velocity is magnitude and direction, so magnitude will be that. So now we also have to get the direction. So we shall come and draw positive horizontal and negative vertical. The next is to get theta, so tan theta is equal to this, implying that theta is 74.02 degrees. Therefore the direction is south, 74.02 degrees east. Then part C, for part C, they ask for the shortest distance between the two cars as they approach O. Now, since they have not asked for time, it implies that the easiest method is the one for crossing. So I'm going to cross initial relative displacement and relative velocity. When I cross, this times this gives you this to 4 decimal places. This times this gives you this to 4 decimal places. So subtract the 2, you'll come up with 193.1864. Therefore, the shortest distance between the two cars as they approach O is given by this formula. So I think remember this formula, you quote it, then you substitute. Now this one was the magnitude of relative velocity which you got in the previous slide. Therefore, when I divide the two, I'll come up with this as the shortest distance. So now I shall go to part C, which requires for time and distance for closest approach. So having looked at questions which ask for either time or distance for closest approach, now we are to look at questions which ask for both time and distance for closest approach. So the methods already seen are the very methods to be used, but in this video, if there are two options, one, a question may first ask for time followed by distance, or it asks for distance followed by time. So in the case where it asks for time followed by distance, these are the two methods we shall stick on. This to get time and this to get distance. But if it first asks for distance followed by time, then we shall use these two methods, this for distance and this will be for time. But all the other methods also work, it's just that these ones are a little brief. So that we shall go through these questions. Question 1 came from UNEB 2009 paper 2 question 16 and says two particles P and Q move with constant velocities of this and this respectively. Initially, P is at a point with position vector this, and Q is at a point with the position vector this. Find part A, the time for which the distance between P and Q is least. Part B, the distance of P from the origin at the time when the distance between P and Q is least. And part C, the least distance between P and Q. So first of all, these are the velocities they gave us. So I'll use them to get the relative velocity. So it will be relative velocity of Q to P is V2 minus Vp. So V2, Vp, subtract the 2 will come up with the relative velocity. Then these are the initial positions they gave us. So relative position of Q to P is RQ minus RP, which gives you this relative position. Therefore, the time taken for closest approach will be, we shall use this formula like we said. So I substitute relative displacement, relative velocity, and magnitude of relative velocity. So dotting, this times this gives you 4, and this times this gives you 20, and this times this gives you negative 90. Then denominator is equal to 30. So magnitude means what is negative becomes positive. Therefore, I come up with 2.2 seconds as the time taken. Then part B, the one the distance of P from the origin at the time when the distance between P and Q is least. So RPT is equal to RP plus VT times VP. So RP is this, VP is that. Then I have to substitute for time. So time was 2.2 seconds. When I substitute, I'll come up with this as the position vector. But the distance will now be, distance from origin will now be got by getting the magnitude, which will be equal to this. Then for part C, they ask for least distance between P and Q. That is relative position is that in terms of T. Then you have to substitute for minimum time taken and come up with this displacement. The distance, you have to get the magnitude. So magnitude will be equal to that, which gives you this, which will be the least distance. Then question 2 came from UNEB 2005 paper 2 question 14 and says a particle P moving with a constant velocity this passes through a point with position vector this. At the same instant, a particle Q passes through a point with position vector this, moving with constant velocity this. Find part A, the position and velocity of Q relative to P at that instant. Then part B, the shortest distance between P and Q in the subsequent motion. And part C, the time that elapses before the particles are nearest to each other. So let's start with Roman 1. So this is what is given. So we shall first get the relative displacements. So substitute for RQ minus RP, which gives you the relative displacement initially. Then relative velocity, substitute for V2 minus Vp to give you the relative velocity. That was part A. Then for part B, shortest distance between P and Q in the subsequent motion. So there you have to use the method of crossing. So I'll come and write the relative displacement and also relative velocity. So crossing means, now these are three-dimensional vectors. So crossing means, how do they cross? First, when you write here I, it implies that you eliminate the I and you remain with these two, which you put here. Okay, then minus j. So this has to be minus j, means you are going to eliminate the j and write this with this, which is here. Then plus k, so you eliminate the k and write this, which is here. Okay, now after that we shall use the method of getting determinant, which will be this times this minus this times this, then also here this times this minus this times this, then here this times this minus this times this, to give you that. The next is simplify. This gives you this gives you this with the negative here, then this gives you this. The next can get the minimum distance now, so I'll have to substitute in this formula. So when I substitute, I'll come up with that, which gives you this as the minimum distance. That is part B. What about part C? So for part C, the time that elapses before the particles are nearest to one another. So we can use the method of dotting. So this dot this over magnitude of V to P. So when I dot, this times this is -5, this times this is +9, this times this is -15. The denominator will be 227. And the end I'll come up with 0.0485. But we don't put the units because in the question there were no units. So now we shall go to question 3, which came from UNEB 2012 paper 2 question 11, and says at 11:45 a.m. ship A has a position vector of this and moving at 8 kilometers per hour in the direction north 30 degrees east. At noon, another ship B has a position vector of this and moving at 3 kilometers per hour in the direction southeast. Part A. Find the position vector of ship A at 12 noon. Then part B. If the ships after 12 noon maintain their courses, find Roman 1 the time when they are closest, and Roman 2 the least distance between them. So here the velocities are given in terms of magnitude and direction, so you have to first make the simple sketches in order to convert them to vector form. So that is velocity of A, then velocity of B is that. So that means that I can now convert them in vector form. Therefore VA will now be this and VB. So at this is VA, but this is VA at 11:45. What about at noon? At noon you have to add on this, it will be RA plus T times VA. So T was 15 minutes, so from 11:45 to noon it is 15 minutes. That's why there is 15 over 60. Now we are dividing by 60 because the time here, if you look at this velocity, the time has to be converted to hours. So when I substitute, I'll come up with this as the velocity of A at noon. So now we shall go to part B, Roman 1. So part B says if the ships after 12 noon maintain their courses, find the time when they are closest. So first of all, we have already got the velocity of A, but the velocity of B we have not yet. So velocity of B still we have to convert this into vector to give you this as the velocity vector of B. That means that now I can get the relative velocity of A to B, which will be this minus this to give you this, Note that we're using 4 decimal places. What about the relative position? Now, the relative position, we no longer use this as the initial position of A because we are starting from none. So we shall use this as the initial position of A. Then the initial position of B, it will be this. So when I simplify, I'll come up with this as the vector, initial displacement vector. Therefore, I can use the dot method to get the time for closest approach. So come and substitute relative displacement, relative velocity over magnitude of velocity, relative velocity. So when I dot, this times this gives you this, and this times this gives you this. Then the denominator gives you this. And in the end, I'll come up with this as the time, so I can change to minutes. After changing to minutes, I can now get the actual time. So 24-hour clock, this is 11:45:0030. So we come up with 12:15. Therefore, in 12-hour clock, it will be 12:15 p.m. That is Roman 1. What about Roman 2? So for Roman 2, they want the least distance between them. So least distance, since we already have time, I'll use RABT. So then I'll substitute initial displacement, relative velocity, then substitute for t, and simplify to come up with this as the relative displacement, but they want distance, so we have to get magnitude. So magnitude will be given by that, which is the answer they wanted. Then question 4 came from UNEB 2018, paper 2, question 16, and says, at 10 a.m., ship A and ship B are 16 kilometers apart. Ship A is on a bearing of north 35 degrees east from ship B. Ship A is traveling at 14 kilometers per hour on a bearing of south 29 degrees east. Ship B is traveling at 17 kilometers per hour on a bearing of north 50 degrees east. Determine, part A, the velocity of ship B relative to A. Part B, closest distance between the two ships and the time when it occurs. So the velocities are given in terms of magnitude and direction, so you have to first make their simple sketches to enable us to convert them to vector form. So that is for velocity A, velocity of ship A, and also velocity of ship B. Is that, therefore, now we can easily convert them in vector form. So VB in vector form, it will be this, and VA in vector form, it will be this. Subtract the two, you'll come up with the relative velocity of B to A. Then for the magnitude, it will be this. We also need the direction, therefore it will be positive horizontal and positive vertical. So tan theta will be equal to this, therefore theta is 15.06 degrees. So we can conclude that the relative velocity is this in the direction north, 15.06 degrees east. That was part A. Then part B, they asked for the closest distance between the two ships and the time when it occurs. So they want both distance and time. So I have to first get the initial positions of A and B. So in vector form RB to A, when I stand at A, I will locate B by moving to the left 16 cos 55, and to the downwards it will be 16 sin 55. All will be negative. This is to the left negative, downwards negative, which gives you this in vector form. Therefore, time I will use the dot method. So substitute this, and then magnitude. Now dotting this times this gives you this, and this times this gives you this. Square this, you come up with this. And then you come up with these hours, which can be reduced to, which approximate to 38 minutes. That is the time. Then for the distance, we have to first get the displacement. So this is RB at t, then substitute for t to come up with this displacement. Then for distance, you remember that you have to get the magnitude. Which is this. And the actual time will be 10:38 AM. And the closest at this distance. So now we shall go to question 5, which came from UNEB 2004, paper 2, question 16, and says, two planes A and B are flying above the Pacific Ocean. Plane A is flying on a course of 010 degrees at a speed of 300 kilometers per hour. Plane B is flying on a course of 340 degrees at 200 kilometers per hour. At a certain time, plane B is 40 kilometers from plane A. Plane A is then on a bearing of 060 degrees. After what time will they come closest together? And what will be their minimum distance apart? Give your answer correct to 1 decimal place. So still here I shall make some simple sketches to convert the magnitude and direction into vector form. So that is for velocity A, and that is for velocity B, and the initial positions. So velocity of A in vector form is this, and velocity of B in vector form is that. Subtract the two, you come up with the relative velocity. The relative position initially can also be got from this sketch. So it means that RAB, I stand at B and I locate A. So when I stand at B, I'll have to move 40 cos 30 to the right, which is positive, and then 40 sin 30 upwards, which is also positive. That's why you see all these are positive. So when I use a calculator, this is this and this is that. So now that I've got the relative velocity and relative position initially, I can use dot method to get the minimum time. So substitute for this, and also for this. So this dotting, this times this gives you this, and this times this gives you this. Then this denominator gives you this. So simplify, I'll come up with these hours, which is the same as this, and that approximates to this because they told us 1 decimal place. Then for relative displacement at any time t, you come and substitute for this and for this to give you this. But you already know the time, so the time we use the one for hours. So substitute the time here to come up with this vector or the displacement. But distance is magnitude, so you have to get the magnitude of this, which is this squared plus this squared, and gives you this. But they said 1 decimal point, so you round off to this. So now we shall go to course for closest approach. So for one body to pass as close as possible to a second body, the course set by that body must be perpendicular to the relative path. For two bodies A and B, it implies that velocity of A dot velocity of A relative to B is equal to 0. Or we can use velocity of B dot velocity of B relative to A equal to 0. Now note that what is here is what we are dotting with. What is here is what we are dotting with. So here, if it starts with A relative to B, we shall dot it with the velocity of A. If it starts with B relative to A, we shall dot with velocity of B. That means that they will be perpendicular. So the course for closest approach can also be got geometrically. So this is for vector approach. But we can also use geometry. So by geometry, let's consider velocity of B relative to A. So in that case, it means we are going to use this. So how do we do it geometrically? There are steps to follow. The first step is to draw a diagram showing the initial positions of A and B. Then step 2 is to reverse the known velocity of A and draw it at position B. Note the position we are drawing it at position B. Then step 3, you draw a relative path for velocity of B relative to A in between BA, in between line BA. So line BA is the line joining the initial positions and velocity of A. We shall see all these ones in the worked examples. So step 4, drop a perpendicular from the head of the reversed velocity of A to meet the relative path. And step 5, use the right angled triangle formed to obtain the required course of VB. So those are the five steps we need. So if a question comes with in vector form, you use this method. If it comes in geometrical form, you use this. So with that, we shall go through these questions. Question 1 says, two particles P and Q initially at positions 3,2 and 13,2 respectively begin moving. Particle P moves with a constant speed of √10 while particle Q moves with a constant speed of 0.5, constant velocity. The units being meters and meters per second respectively. Find the course P must take in order to pass as close as possible to Q. So this question is in vector form, therefore we shall use the vector method. So we are given RP as that and RQ as that. Then magnitude of VP is that and VQ as that. Therefore we shall come and say that let VP be equal to XY. Therefore VPQ is equal to VP minus VQ, which gives you this. So for P to pass as close as possible to Q, the course set must be perpendicular to the relative path. Therefore, Vp dot Vpq is equal to 0. Think you remember that we said if it's what starts here, what is here is what we dot it with. So we shall come and substitute Vp and Vpq equal to 0. Then dot, this times this is x squared, this times this is y squared minus 5y equal to 0, and that is equation 1. But we also know that Vp, magnitude of Vp is √10. Therefore, we'll come and substitute Vp is this, which is x squared plus y squared under root. Then square both sides to come up with equation 2. Now we have two equations and two unknowns we have to solve simultaneously. So when I substitute equation 2 into equation 1, I'll come up with this. So where there is the whole of this, I'll replace it with 10. That means that y is equal to 2. Now from equation 2, I can substitute for y and get the value of x. Therefore, VP is equal to this. Now we are ignoring the negative sign because this should be positive. So the direction, positive horizontal, positive vertical. Therefore, tan theta is equal to root 6 over 2 and theta is 50.77. The course set by P will be north 58.77 degrees east. So now we shall go to question 2. It says that motorboat B is traveling at a constant velocity of 10 meters per second due east, and motorboat A is traveling at a constant speed of 8 meters per second. Initially, A and B are 600 meters apart, with A due south of B. Find the course that A should set in order to get as close as possible to B. So this is in terms of magnitude and direction. Therefore, the easiest method is the geometrical method. So we shall come here and first look at the velocity whose direction is known and draw it and then reverse it. So VB is known, so we shall reverse it to be in this direction. Then from there, the next step is to locate the initial positions of A and B. So they said A is due south of B. So when I stand at B, A will be south of it. And the distance was 600 meters. Okay. Then when next is to get this reverse velocity, so it is the velocity of B, meaning it will be put at position of A. So you shall come at position of A and put the reverse velocity of B, which is 10 meters per second. Then from there, we shall draw a relative path between this velocity and this line joining B to A, which is that. So we draw it anywhere in between the two, and that will be the relative velocity. The relative velocity will be along the relative path. Then next is to drop our perpendicular from the head of this reverse velocity to meet the relative path. So I'll come and drop a perpendicular to meet the relative path, and that will be your VA. Now this is the right angled triangle which I should use to get this direction. So the direction my interest is to get theta. So this theta is equal to this by geometry, and the good thing, VA is known as 8. Therefore, with this there will be opposite and hypotenuse, which is sine. Therefore, the angle is 53.13 degrees. Therefore, the course set must be north 53.13 degrees east, and that's what they wanted. Then question 3 says, two aircrafts A and B are flying at the same altitude, with A initially 5 kilometers due north of B. B is flying at a steady 300 meters per second on a bearing of 060 degrees. If A flies at a constant speed of 200 meters per second, find the course that A must set in order to fly as close as possible to B. So we shall get the velocity whose direction is known and reverse it. So this direction is known, so we shall reverse it to give you this reverse velocity. Then from there we shall locate the initial positions of A and B. They said A is 5 kilometers due north of B. So when I stand at B, A will be due north of it. The next is this is now reverse velocity of B, so it will be put at A. The next is to draw a relative path in between VA, in between this reverse velocity and the line joining the initial positions. So let's do that. And on that relative path, that is where the relative velocity lies. Then next is to come at the head of the reverse velocity and drop a perpendicular to meet the relative path. And this will be the velocity of A. So now I have a right angled triangle, and the good thing, VA is known, it is 200, therefore I can get the value of theta using cos, because it's adjacent, this is the hypotenuse. Therefore theta will be 48.18 degrees. Therefore alpha will be, remember the whole of this is angles on a straight line which add up to 180, therefore alpha alone will be 180 minus the sum of 60 plus 48.18, which gives you 71.81. Therefore the coset will be south 71.81 degrees east, and that's what they wanted. Then question 4 says ship A is moving with a constant speed of 18 kilometers per hour in the direction of north 55 degrees east, and is initially 6 kilometers from a second ship B, the bearing of A from B being north 25 degrees west. If B moves with a constant speed of 15 kilometers per hour, find the course B must set in order to pass as close as possible to A. So shall come and reverse the velocity whose direction is known. So this 18 kilometers per hour, the direction is known, so we shall come and reverse it. Then from there we shall locate the initial positions of A and B. They said ship A is initially 6 kilometers from the second ship B on a bearing of, and the bearing of A from B is north 25 degrees east, which is this. Then from there I will come and get this reverse velocity. It is the reverse velocity of A, meaning I'll put it at B. So let's do that. Okay, then after that I'll draw a relative path in between that reverse velocity and the line joining AB. So let's do that. And that is where the resultant velocity will be. Then from there, at the head of the reversed velocity, I will drop a perpendicular to meet the relative path. So let's do that. And this will be the velocity of B. So I'll use the good thing, the velocity of B, the magnitude is known, meaning I can use now SOHCAHTOA. So with this angle, this is adjacent, meaning I'll use cos. Therefore theta will be 33.56 degrees. Alpha will be, remember the whole of this is equal to 55, therefore alpha alone will be 55 minus theta, which is 21.44. Therefore the coset will be north 21.44 degrees east. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be on moments and couples. So if you have not yet subscribed, please click on the subscribe button below this video so that you receive updates when the next video on moments and couples has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so that we can all benefit as a family.